Thank you. All right, great. So basically, part of the objectives of this class will be salient reviews on lateral edge pressures. I need to state categorically that whether you are designing sheet pile, you are designing retaining wall, all of them are embedded in your understanding of lateral edge pressures. If not, you just end up cramming the formula, and then who knows if you have a soil that is submerged, a soil that is partly submerged, and all those technical details. And the question is quite easy, but then if you are not exposed to it, it becomes a problem. So we have to do a salient reviews on lateral edge pressures, and then brief theoretical background on retaining walls. Fully aware that we're having OBJ tomorrow. Just speak briefly on retaining walls. So you probably don't need to go back to your slide after the tutorial. Then principles of the design of retaining walls, we speak about that, and then we move on to sample design exercise. And Michael Obaming, are you on the course, sir?
Yes, sir.
All right, great. Please, I made you co-host, so I'll be able to admit others as I'm teaching. So can you hear me do that, sir? Can you hear me?
Yes, I can hear you.
All right, please, can you hear me do that? Admit people as they are joining. All right, thank you so much. Yeah. All right, let's get to it. Review of lateral edge pressures. As we all know that this was a course that we did, a topic we did under CEG 405. So I'll just run through it. But to begin with, what are retaining walls? Retaining walls are structures built to retain vertical or nearly vertical edge banks or any other materials. Basically, they are vertical wall, obviously gigantic in nature, and to retain either water, earth. It's dependent on the purpose. You can have earth dam, you can have water dam, amongst others. But there's a common trend amongst them, whether they are retaining earth, whether they are retaining water, they are all resisting lateral edge pressures from earth bank, waters, or any material. So the retaining material itself that they are probably preventing from getting to the other side of the wall are called backfill. So the way it works is that we have a gigantic vertical wall, trying to prevent some set of materials to cross over the other side. And then that particular materials will be probably exerting, substantial lateral edge pressures. So we have to design with the mindset that these lateral edge pressures must not make the retaining wall in question probably fail, amongst others. So moving on to lateral edge pressures, there are two classical edge pressures theory. First is the Coulomb's edge pressure theory, and the second is the Rankin's edge pressure theory. For those of us that probably read retaining wall or sheet pile, we must have been seeing active edge pressure, passive edge pressure, how to calculate them, probably how to get the centroid axis, amongst others. But it's crucial to state that and calculating your active edge pressure theory, calculating your passive edge pressure theory is contingent on different questions requirements, these different design requirements. Like I said earlier, some questions will probably be submerged in water. The one we did in class is not submerged in anything. It's just you are retaining an earth dam. So I think that is quite straightforward. But in the course of expositions during this class, I will try my best to speak briefly of what you are expected to do if you have probably a material that is submerged in water and you are trying to retain it from getting to the other side of it. Now that will make me to start with us Coulomb's edge pressure theory and Rankin's edge pressure theory. Now, what Coulomb's edge pressure theory would do for us is that yes, we need to have a proper understanding of what our active edge pressure. We need to have a proper understanding of our passive edge pressure. But all of the formulas guiding the active edge pressure and passive edge pressure all came from Coulomb's derivation of the pressure at rest condition. Now, once we probably learn briefly or revise briefly the Coulomb's derivation of the pressure at rest condition, we can easily infer the pressure, the active edge pressure or the passive edge pressure, which we definitely use in our subsequent design. So our active and passive edge pressures, let's consider a rigid retaining wall with a plain vertical face, backfill with a cohesionless soil. Now I'm going to display the diagram soonest. So when you are backfilling with a cohesionless soil, in that case, you are saying that you are neglecting the frictional properties of that particular soil, not the retaining wall itself. I think I need to make that clear. So if I say I'm backfilling, a retaining wall or a vertical plane with a cohesionless soil, is the soil itself that you are neglecting the cohesion rather. The friction is actually what you are considering. So when you have a cohesionless soil, you have the cohesive properties of that particular soil. You are neglecting and you're only considering what? Your friction. That being said, I think I have, yeah. So as displayed here, so this is basically what we have. We have a vertical wall, and then this is your backfill that I indicated with this, and then you are having your wall here. This particular wall itself is a section of the retaining wall. Then you have your backfill, and also you have your ground level here of the retaining wall. Now, If the wall does not move, even after backfilling, the pressure exerted on the wall is termed as the pressure at rest condition. So what we're trying to explain here is that, okay, you have a retaining wall and then probably is retaining what? Earth dams, is retaining air dams, or is retaining water. Now, if the lateral earth pressure exerted from the backfill does not cause any motion on the retaining wall, that is, it doesn't make it to deflect probably or rotate to the left or rotate to the right. In that particular scenario, we are saying that what? The lateral earth pressure acting on that retaining wall that did not cause any deflection on that retaining wall is the pressure at rest condition. This may be sample OBJ question, so that is why I'm sticking with this. Moving on, suppose the wall gradually rotates about point A and moves away from the backfill. We're going to say a grammatical explanation now. Now you have this retaining wall. Now the first diagram I have here is just a retaining wall at rest that is not moving. A retaining wall with a backfill. That is, the backfill is not sufficient to cause deflection or rotation at a particular point of that wall. Hence, we say that pressure, the lateral earth pressure caused by the backfill at rest condition is called what? The pressure at rest condition. Now we're not considering that scenario that, okay, let's assume that what? The wall gradually rotates apart point A. This point A, right? So if the wall is rotating about point A and moves away from the backfill. Now, from the wall moves away, this is quite commonsensical because I'm trying to, I'm applying backfill at this particular region. So it's quite logical for my retaining wall to deflect towards this other side. If you see this particular arrow now, because you can easily infer that what the lateral earth pressure of the soil or the water or whatsoever you are retaining is the one responsible for the deflection or the brief rotation of this particular retaining wall. Now, in that particular condition now, as the movement, obviously, it keeps on displacing, but it's going to get to a particular point. As this particular body is displacing away from the soil, the backfill, one thing will happen is that what? The contact surfaces will be reducing. And obviously, you know that what? Your pressure is what? Force with respect to area. Now that your contact surface is reducing, so you can easily say that what? If this is moving away from the backfill, mind you that what? The backfill itself is what is responsible for the what? For the brief rotation of this retaining wall. Because it's moving away, I can easily say that what? Okay, the pressure acting on this retaining wall must be reducing. Because it is moving away, because pressure is force with respect to area. Now, no matter how small it is, there's going to be a reduction. So at a particular point, the movement will not happen again. That is, at that particular point, the reduction of the pressure will reach a constant value. The reduction of the pressure will reach a constant value, and that is what we call what? The active earth pressure. I'm going to recap briefly for OBJ purpose. I started by saying that consider what? A rigid retaining wall, right? Acted upon by a backfill. But this backfill is not sufficient to cause motion. That was the first diagram. Now, because this backfill is not sufficient to cause motion, the lateral earth pressure exerted by that backfill on the retaining wall that is not causing rotation, we call it what? The pressure at rest condition. Now, we now consider the second diagram here. That is, this second diagram, also you're having what? A soil, that is a backfill, acting. But in this particular, scenario, the wall itself is rotating about point A. In this particular direction, look at the arrow that is away from the soil. And I said that is quite commonsensical, that is quite logical, because if I'm pushing something away, it's supposed to move away now. So you can easily infer that what? The deflection of this particular retaining wall is being caused by what? The effect of the backfill acting on it. Now, obviously, because of the fact that this thing is moving away, at a particular point in time, you expect that what? The contact surfaces will be reducing. At first, there was a close contact. Now, because of deflection caused by that same backfill, there'll be a brief reduction in what? In contact between the backfill and the retaining wall. And as it's moving, the pressure keeps on reducing until it gets to a constant value that it cannot move again. That particular value is the minimum possible. And that's what we call what? The active earth pressure. And based on what I have on the screen now, I said it is called active pressure since the weight of the load is responsible for the movement of the wall. Which I think that was why I used the word commonsensical, because it is crucial to know that for active earth pressure. Sorry, Mike, I may miss that person. Thanks. Now, for active earth pressure, the weight of the backfill itself is responsible for the movement of the wall. It is crucial you have this by heart because it's a likely OBJ question. Now, moving on. Okay, before we move on, if the wall is smooth, then this particular pressure. Now, obviously, there's a free body diagram here. You have your retaining wall, causing this deflection. This is the short dashes I do here. Now we're not trying to draw the free body diagram of this particular what of the effect of that backfill. Now you may want to ask me that why am I representing why am I putting the arrow on the other side? Always remember that what the line of action of a force is continuous. So me putting it here does not really matter. What actually matters is that I'm representing that what it is acting on this body, and I also indicate my rotation aspect that what it is moving towards what away from the backfield, and that is the cause of the discussion, that the backfield is making it to move away, and the weight of that backfield is what is causing that rotation. Hence, it is called active earth pressure. But if the wall is smooth, this particular angle, which we can say the angle of internal friction, is basically normal. It's going to be at right angle degree. But if the wall is not smooth, obviously, you are going to have an angle, and is dependent. You'll be given your question. So you need to also know that what if the wall between your words, if your wall is smooth, the active earth pressure, that is, if there's no friction, the active earth pressure will always act normal to the plane vertical and to the plane vertical face that is actually rotating. Who knows if the man can ask? Now, the angle is called what? The angle of friction, like I said earlier. Now, let's consider a separate scenario. If the wall is now rotated about A, permits me that I'm quite fast. I'm reviewing lateral pressures. This is actually a topic, but it's crucial in retaining wall. Now, if the wall is now rotated about A towards the backfield, not away from the backfield, the actual free plane of ADC is also a curved surface. Let's look at the diagram. Now, we have this particular diagram, very similar to the other one. Now, the difference is that this arrow is now rotating inside. Now, that is quite ridiculous, because you obviously, if you have a weight of your backfield, you are expecting that the weight should make it move away, not enter. But this is another case scenario. Instead of it to be moving away, it's rotating inside the backfield, towards the backfield, in that particular direction. Now, if I'm moving towards the backfield, one thing will happen. I'll be increasing my contact surfaces with the backfield, even not even fully submerged, right? Now, as I'm increasing my contact surfaces, like I said earlier, that your pressure is forced with respect to area. Now, as you are increasing your contact surfaces, the pressure in this particular case will keep on increasing until you get to the maximum point possible. And that maximum point possible is now what we call the passive earth pressure. And it is called passive because it is very evident in the diagram that if this thing is moving towards the backfield, then the backfield is not responsible for the motion of that retaining wall. Because if the weight of the backfield is responsible for the motion of that retaining wall, it's supposed to move away. And that's why we don't call it active. We call it passive. And like I said, this one keeps increasing until it gets to the maximum possible. Why for active? Active keep decreasing until it gets to the minimum possible. So I have on the screen that the pressure on the wall increases from the value of at rest condition to the maximum value possible. The maximum pressure that is developed is called the passive earth pressure. The pressure is called passive because the weight of the backfield opposes the movement of the wall, which is very important. Now, this is just basically, based on probably research amongst others, but then we can actually, infer this mathematically based on our experience in civil engineering, that the distance you require to get to your passive state is considerably larger than the distance required to get your active state. And I think we can easily answer that. Even probably this was getting from experimental research. Look at it. Normally, I'm pushing something away. You're supposed to move away. Now, you are not moving away. You are moving towards you are moving opposite the direction of the force. Now, at first, you need to overcome the force that is pushing you away before you can now also move. So it's very evident that for us to reach that passive state, we need to apply considerable amount of displacement before we get to that maximum passive pressure possible, because you first have to overcome the effect of the weight that would tend to push you away. Now, you now want to move towards the direction, which is quite, like I said, which is quite very, very not common sense to me, but it can happen based on what we have here. So that is why the displacement required for the passive pressure is considerably larger than that required for the active pressure. So let's move as fast as we can. Now, all of these things that I've probably explained earlier will now make us have a proper understanding of the calculation of our active earth pressure and our passive earth pressure. Probably before I move on, maybe someone should just signify if I'm not saying jargon since if you are still following. All right, great. Oncho said he's lost. Fantastic. Oncho, when you join the class, if you don't meet yourself.
We are still following from here on my side. Yeah.
Alpha, Oncho, when you join the class.
Bro, I'm not getting shit.
All right, fantastic. Fine. Okay, I'm too fast. Apologies. I will slow it down. This is a full topic. That is why. Okay, let me just do a brief recap. I'll apologies so far. I hope everyone are also following. If you have any problem, please feel free so that we can be on the same page.
We are following. No.
All right, great. So on I started by this defining retaining wall. I mentioned there are two theories. These are these are basically theoretical jargons, all right? So what I just tried to do was that you can have your retaining wall. Let's say this diagram is indicating my retaining wall. Now at this particular aspect, that is the right-hand side, if you can see my mouse hovering over here, now we have a backfill, but the backfill is not causing motion. The backfill is not causing this wall to deflect. That is the lateral earth pressure. Like I said earlier, all backfill will always exert a lateral earth pressure horizontally towards your wall. Now this lateral earth pressure is not sufficient to cause deflection. That is, the wall is still at rest condition. So that pressure, we call it what? The pressure at rest condition. And I move on by saying that, okay, what if you now have a situation whereby deflection happens or rotation happens? Now, it can either happen in two ways. Is either this particular wall moves away from the what? From the backfill, which I said is quite commonsensical because my weights obviously should push it away. All right. But we also have the wet scenario whereby the wall will not move away. It's going to move inside the backfill, towards the backfill. And those are the two scenarios I tried to analyze. I said that, okay, I think I have a diagram here. Now, this is a diagram representing that this is moving away from the arrow. If you see the arrow, this arrow will be towards. So this weight of the what? Of backfill is actually the one responsible for moving it away. Because that is very logical to actually infer that this weight, because a weight is acting at this particular side, horizontally, obviously now, the effect of this weight, is going to produce some horizontal forces also, lateral earth pressure. It's going to move this away. Now, moving this away, they are calling it active earth pressure. Why? Because the weight of the backfill itself is responsible for the what? For the rotation of the what? Of the retaining wall. That's why we call it active. Now, I also stated that you need to know that as you are moving away from the backfill, your contacts will keep reducing. And if your contacts keep reducing, your pressure must be reducing because your pressure is what? First with respect to what? With your area. Now, because your contact surface is reducing, obviously your surface area is also reducing. So as this is moving away, the pressure, that lateral earth pressure on this retaining wall will keep on reducing until you get to the what? To the minimum possible. Now, that minimum possible is what we call what? The active earth pressure. And I think I now move on to the next. And I also mentioned that, okay, this angle can be, this particular angle represents your angle of friction. It can be normal. Normal means it can be 90 degrees or it can be any angle. It is normal if we are sure that what our plane is what is a smooth surface, that is no friction is acting there. Then I move on to the second aspect of the class where I say that, of the lateral earth pressure rather, that what if it's moving away? Now, this is quite weird, like I said earlier, that what your lateral earth pressure is supposed to push it away, but now it's not moving towards it. In that particular scenario, because it is moving towards it, the contact surface keeps on increasing. As it is increasing, obviously, your area keeps on increasing and your pressure keeps on increasing. So as opposed to your active earth pressure, the pressure will keep on decreasing. This is now passive earth pressure because this is moving towards the backfill. Now, contact will be increasing. As you are moving towards it, your pressure will be increasing until it reaches the maximum possible. That is, there's no more motion. It's no more moving towards it again. That maximum possible is called the what? Passive earth pressure. And I actually infer personally that, okay, maybe they use the word passive because this is actually a weird scenario. Why would something be pushing it to the right and is moving to opposite it? That's basically what we're trying to do. So we call that the passive earth pressure. And for your design of retaining wall, we don't really use passive earth pressure. We use active earth pressure. But for sheet pile, we use both of them, both active and passive. So that's basically all I think I've said. And I said that, okay, it will take considerably larger displacement or larger effort to get to your passive because, something is trying to push you away, but you want to move as opposite that direction of what is pushing you away. So you have to ask, it's going to take longer effort for you to actually achieve that. And that's why I said that the displacement of your passive pressure is far, far greater than or considerably greater than the displacement of your active pressure. I hope this is clear, sir. So let's move on lateral earth pressure at rest conditions. So let's just generate the necessary formula and consider a prismatic element E in this. We have this is a sample retaining wall, but now we've drawn it with the mindset that, okay, we have a backfill with the pressure distribution in mind. We're going to get there. But what we are basically after is that you have your retaining wall. Now, this is the backfill. This particular, this inclined line like this, that they are intersecting each other indicates backfill. Now, I'm not taking a prismatic element within that backfill. It's like we're saying that let's take a sample of that backfill element. Now, we're taking a sample of that sample element. Two forces will be acting on it. Obviously, we're going to have your vertical pressure, and you're going to have your horizontal pressure. Now, don't forget that your vertical pressure can be your unit. Your vertical pressure from our knowledge in civil engineering so far is said to be your unit weight with respect to your height. Don't forget, for you to have a proper understanding of that, for those that probably have a problem with that, your unit weight unit is what? Kilonewton per meter cube. So if you multiply kilonewton per meter cube with your depth or your height, your depth unit is meter. So meter will cancel part of this. So you now have what? Kilonewton per meter square. And that is why it's called what? Vertical height pressure. Now, this is vertical pressure because the Z we are using is what? Is vertically. Now, this lateral height pressure, which is majorly which is one of the most important things we consider doing what retaining wall design is, how do we generate it? What are the basically the formula we use? Now, it is crucial for you to know that if this particular backfill, let's say it's homogeneous altitude, you are using clay or you are using silt, that the rate of increase between your vertical pressure and your lateral height pressure are linear. All these things I know about talking about, we get OBJ tomorrow. Now, the thing is that the rate at which your vertical pressure and your lateral pressure increase are linear. That is, let's say you have a positive slope or what? A negative slope. That's basically what they are saying. So in that case now, we can say that what? The ratio of my vertical with respect to my horizontal is a constant. I will repeat that. That obviously I established the fact that, okay, on every part of your backfill, you're going to have your what? Your vertical pressure, you're going to have your what? Your horizontal pressure. For your vertical pressure, we can easily generate that using what? Unit weight times what? Height. Now, for your lateral height pressure, we need to deduce the formula of lateral height pressure. Now, it has been proven that if the backfill is homogeneous, let's say it's clay or silt or fill, the relationship between your vertical pressure and your lateral height pressure is linear. That is, hence, we can say that what the relationship is definite. You can easily get the slope. Your change y related to s can be 2. So we can say it's a constant. So throughout that particular backfill is going to be what? A constant. Hence, we can say that based on what I have here, if the ratio of my horizontal with my vertical is constant, don't forget that what I said my vertical pressure is what? Unit weight times what? Times my depth. So I can relate this and what? Arrive at this, which is what? Pressure is what? K naught times what? Unit weight times what? Depth. Now let me take that, more simpler mathematically. You have your lateral pressure divided by your what? Your vertical pressure. Now, your lateral pressure, obviously, your vertical pressure will substitute based on what we got earlier. And this K naught is the what? Is the constant of the ratio, which I explained that if you have an homogeneous soil. Now, this constant itself is called the coefficient of earth pressure at rest condition. So you know that when I studied, I said you can have at rest condition, you can have active earth pressure, you can have what? Passive earth pressure. The rest condition was the one that the retaining wall is not displacing, which I mentioned earlier. Now, if you do your solid of formula, you are going to get your what? Your lateral height pressure should be what? K naught times unit weight times what? Times your what? Your height. That is the height up to the level you are considering. Now, so let's say your height is now h. Obviously, if your height is h, you can see that what? Your lateral height pressure at that particular place is what? K naught. K naught is your what? Is your coefficient of earth pressure at a rest condition times unit weight times what? Height. Now, let me explain. This is very, very vital. Now, how do we arrive that the distribution of the wall is given? Now, let me do this. It is crucial to know that whenever you have a retaining, an edge down or any backfill on a retaining wall, the distribution is always triangular in nature. It's always triangular. The only one that there are only two separate scenarios that are not triangular, they are rectangular in nature, and those are your surcharge and your water, which we are going to actually treat. Because I know that our retaining wall will be designing a particular retaining wall that has a surcharge and that also has what? Edge down. For whenever you have your backfill, once it's not a surcharge or it's not water, your pressure distribution is always rectangular in nature. Now, that being said, don't forget that your lateral height pressure will be increasing as your height is increasing because your K naught is a constant, your unit weight is a constant. The only thing that varies is your height, and that is dependent on you. So if I want to look for my pressure at this particular height, let me call this height Z. Now, let's say the full height of the retaining wall is H. So the pressure at the ending of the retaining wall will be what? K naught alpha what? H, which should be the what? Highest possible. Now, this explains why it is triangular in nature because it keeps on increasing as your height is what? Your depth is what? Increasing. That's why we have the triangular in nature. Now, obviously, from our knowledge of, from knowledge of bending moment, we can say this is a varying load. Now, if you have a varying load, how can you convert your varying load to a point load? Obviously, all you have to do is what? You take the area of the distribution, and the distribution we're having here is what? Is the triangle. So if I take the area of this distribution, I'm going to have what? Half times base times what? Times height. My base, obviously, I've explained is what? K naught alpha H, which is what? The maximum pressure possible, maximum lateral height pressure possible. Don't forget, lateral height pressure is horizontal pressure. That is why it's horizontal length. Now, obviously, your height is what? H. So by the time we do half times K naught half H, times what? H, you are going to be arriving at this, which is the total pressure. Now, this total pressure, where is it going to be acting? From your knowledge of centroid, if you're having a triangle, from the base is going to acting at what? At H/3, and from the tip is going to be acting at what? 2H/3. These are what we've done so far, from our previous experiences. So that's basically what we have here. Okay. So we've been able to generate that, and then, okay, I think I repeated the slide. So I think the discussion also knows that what? Your K-naught, you don't need to even, all this proving I'm doing is just for the purpose of OBJ or proper understanding. Know that what? Your K-naught is what? 1 minus what? Sine alpha. And where your sine phi, rather, your sine phi will be given is the coefficient of friction that will be given what in the question. That is your K-naught. Now, I need to also state that what, when I started, I said we have 2 theories of lateral height pressure. We have your Coulomb theory, you have your Rankine theory. It was Coulomb that helped us to derive this particular one that we just finished, that is the pressure at rest condition, which is what? K-naught alpha what? Alpha H. But Rankine said, okay, the difference between your pressure at rest. Now, look at, I have PA. So what's basically the basic difference here is just that when you have K-naught for pressure at rest, you're now having active pressure. That is, your active bed pressure is now what? Ka. Ka is the coefficient of the active bed pressure, and it is given by 1 minus sine phi over what? 1 plus sine phi. You just have to know this by heart. Now, also, you can easily deduce your what? Your passive pressure to be what? Kp what? Alpha what? Alpha Z. So that is basically, the foundational mechanism of where lateral height pressure is crucial in retaining work. Now, we'll be moving on to an important aspect, that is, what if we have a situation whereby our backfill is submerged in water? I must particularly state that the example the man gave us in class is neither submerged in water. It only has what? A surcharge on it. So we'll be moving on to an aspect whereby we treat if your S dam or your backfill is submerged in water, and also if your S dam is active with a surcharge present. So it can be 2 scenarios, because in class now, I gave us an example of surcharge. They may bring in exam, the one that is submerged, because we're actually expected to know that from our year first team of work. Before I continue, like any problem, any confusion, you want me to probably explain or go back?
Taiwo, can we get the material so we can follow?
All right. Then I'll have to pause the class for like some minutes. Let me send you WhatsApp. Is that fine?
Thank you, please.
Okay. Okay. Just a minute. I'll send the PowerPoint like that because I'm here to convert it to PDF. Okay, I've sent the PowerPoint. After the class, I'll convert to PDF and send the PDF format. All right. Okay. I also believe everyone is following. So let's quickly run through this so we can move to the main aspect of the class. Active pressure. So let's assume that your backfill now is not submerged. It's not submerged in water. Let's say that what is is fully submerged in water. That is, water is basically covering your backfill. So if a retaining wall is supporting, your retaining wall can support either water, can support earth and soils, can support earth materials or any other thing. But there's some situation whereby your retaining wall will be supporting soil or earth materials that are also fully submerged in water. Now, the only thing that you just have to take note of that one is that, okay, now that water is now, it has now come into consideration. My pressure, my total lateral height pressure will not be caused only by by the soil. Now it's going to be an addition of of the effect of water and the effect of the material. That is the simplest explanation of it. Now the remaining we'll just be doing is the mathematical explanation. Now that is we have. Okay, now obviously this is your water table. So what this signifies that, okay, you have your soil. This soil is fully submerged. That is why you see that your water table is directly on top of the retaining wall. Now, look at, based on the points flow, they try to take the resultants, obviously acting at H/3 of your at h/3 of your triangular section. So obviously, if you take that, you have your PA plus PW. PA is your what? Your active earth pressure, and your what? Your PW is your what? The pressure due to water acting on the what? On the body. So, like I said earlier, the earth pressure due to submerged weight, and the what? The lateral earth pressure due to what? Due to water. Now, it's crucial to state that what? At any point, don't forget that now I need to also state that what? We are treating active earth pressure. So you'll be seeing PA, because that's what we'll be using in retaining wall design. Now, like I said, your active earth pressure, your resultant pressure acting is going to be PA plus PW, that is pressure due to what? To your earth material, and also pressure due to water. We've derived this to be what? Alpha, unit weight times depth times what? K. Now, if you see that this unit weight is having what? Subscript B, what is basically means that what? This is not the unit weight of the soil alone. Like, the former soil we actually treated, it wasn't submerged. This is the unit weight of the soil in water. So your unit weight of the soil becomes different when it's submerged in water. It's different from when it's not submerged in water. So you'll be giving that in question, obviously. And then you have your height, you have your K, because we are treating what? Active earth pressure. Now, this other aspect, just like the way we actually derive what? We derive vertical what? And vertical pressure. You need to also state that what? For you to easily, the way to derive the lateral earth pressure of what? Of water is basically what? Multiply the unit weight of water with the level of water. So once I multiply my unit weight of water with level of water, I will get the lateral pressure caused by that water. In this particular scenario, we are not having anything like K naught, K, because water, this is basically what we've been doing since how you can convert your what? Your unit weight of water, you can convert it to your what? To your pressure. Just multiply by what? By your height. So now we've gotten our pressure due to water, we've gotten our pressure due to what? Due to the unit, due to the what? And earth material that is submerged. So the addition of both of them will give you what? Your resultant what? Active earth pressure at any point. I need to also state that the same way I mentioned earlier that what? This your small letter PA is dependent on your height. That is, as I'm going down, it's going to keep on increasing. Now, I think this diagram is quite inverted. So in this particular scenario now, let's say as you are going up, if you check from this particular and sharp point, as you are going up, the horizontal line keep on increasing. That denotes that what? Our pressure keep on increasing. And I explained earlier that what? Is because your what? Your increase in your active earth pressure or pressure due to water is dependent on your height. So the deeper your retaining wall, the higher your what. Now there's also a need, because it's a varying load, obviously, you can't analyze with each of them separately. You need to calculate a resultant. This is a triangular varying load. So you have to take the area. Taking the area is what? Half base times height. At this particular point, it's going to be your pressure, your active pressure will be what? Alpha B K H. And this particular, why your pressure of water will be what? Alpha WH. That Z will turn to H. And your Z also turn. That is basically what we are doing. And then you are going to see it now. So now we are now having what? Basically, all they are doing is that what? They are taking what? Area of the what? Of the triangle. So I need to state that even though I drew this as just one triangle, your pressure distribution as separate triangle, because the earth pressure will have its own what? Pressure distribution, which is triangular in nature. That is the pressure due to submerged weight of the soil, and also the water will also have its own pressure distribution, which is also what? Triangular in nature. Both of them are triangular in nature because they varies with what? With height. And that is explain why I think I should have the diagram here. Okay, fantastic. So basically, let's say that this is your lateral earth pressure. This is for what? Due to the earth materials, and this is due to the water. So the distance here is alpha HKA, because as the height as the depth is increasing, your pressure increase, and that's basically what we have here. And that's why we have this thing, and the formula. That is basically it. Now, this particular one we are treating now is applied in the example the man gave us in class, which should be treated subsequently. Now, what if you have a surcharge acting on the what? Acting on the retaining wall. Now, you know that when I've started by saying that all my pressure distribution have been triangular in nature, they've been varying. Whenever you have a uniform surcharge, the word uniform cuts it off. Now, this one is not varying. Your pressure distribution is going to be rectangular in nature because it is uniform all through. So let's say when we have UDL on the P, when we have UDM on the B, obviously, you know that we just take what? We take the area of normal triangle, and that will be your, of normal rectangle, rather, that will be your. So what you have to understand that the pressure distribution of this will be different. Now, don't forget that what I have on the screen, I have partly submerged with a uniform. So this is actually three scenarios. That is, this is partly submerged. That is, some part of the soil are in water, while some parts are not in water. If you check where my mouse is hovering, the one I indicated alpha B, that is a place in water, while the one on top is not in water. Now, you cannot see this Q per unit area. This is the uniformly distributed load acting on the retaining wall. So you are considering three effects. First, you are considering the effect of what? Of your submerged earth pressure. You are also considering the effect of the one that is not submerged, that is the one that is actually above the water level. And you're also considering the effect of what? Of your unit area. It's not complicated. Just always remember that what? One thing you have to remember that we don't have, the way we do not have K naught for water. Water is just what? Unit weight times what? Times height. For your pressure due to your what? Your uniform load. Because you are considering the active effect of that pressure, it's just basically what? Ka times Q. Whenever you have a surcharge and you want to calculate the pressure, your pressure is just basically what? K times Q. Your K is the what? Your coefficient of what? Active earth pressure. And that Q itself is what? Is the UDL that will be given in per unit area or anything they want to give you. And you have the normal derivation of others. So all I just want you to take note here is that the distribution here is not going to be half base times height. It's just going to be your what? Your formula for your pressure, like I mentioned earlier, is what? QKA. QKA is your lateral height pressure. When you convert, for you to convert your surcharge load into your pressure, just multiply it by your what? Your active earth pressure. By the time you multiply into your active earth pressure, you are going to get your what? Your lateral what? Your lateral earth pressure. Now, if you check the horizontal lengths are uniform all through, that shows that what? That is exactly why it's not triangular in nature. These are uniform all through. This simply shows that what? Everything acting, the lateral earth pressure caused by what? By Q is uniform along the retaining wall, irrespective of the depth. And that's why we're not considering depth here. So you know that you're now having what? First, you're having your surcharge, you're having effect of your submerge amongst others. This is actually not the content of the course. So it's not really what I just want you to take note here is that what? Your pressure caused by this is QKA AB plus this and this. By the time you're not taking your resultant pressure, which is what you'll be taking when you're designing the retaining wall, is that it's just your normal area. If you take area of a rectangle, it's going to be what? Base times what? Base times height or length times breadth. So the base here is QKA times H, and that is why we're having QHKA here. QHKA here. And these other two are just what? Are probably what? Triangular in nature based on what we've explained here. Now, I think that's basically
explain the second diagram.
This particular diagram, right? This particular one.
The trapezium and the triangle.
All right, fantastic. Since you want me, I actually want to flash it because it's not the core content, but let me explain. Now, if you look at in this particular, this is for the soil. This is for water. This last one is for water, so you know water is triangular. But the soil you are having, the soil is partly submerged, which implies that what? Some part of the soil are inside water, while some part of the soil are above the water. Now, the one that is above the water, obviously, let's say this is where the depth, obviously. Look at where my mouse is over. This is where the water level is. So the pressure distribution for the soil that is not submerged, that is not inside water, is just this triangle. Right? Now, the one that is inside, that is submerged in water, is going to have its own separate triangle too. Now, this is the point. Look at the pressure distribution of this one stop here. Now, because you're not submerging it, there'll be an increase in your lateral earth pressure because you'll be feeling the effect, the soil itself will be feeling what? The effect of weight, and you'll be acting more. So the pressure will also be what? Will also be triangular and what? Will also be triangular. So this second triangle aspect is your effect. But now, you now want to explain this other rectangle. This other rectangle simply shows you that what? This particular aspect that is not submerged in water, that has this lateral, is not submerged in water. So it keeps on increasing with depth until it gets to the water level. Immediately it gets to the water level, that particular soil that is not submerged in water is going to produce, this is the maximum possible it can produce all through the retaining wall. So you get, now, the reason why, because this is the up-submerge effect. This is the maximum up-submerge effect. So from that point of your water level, it's going to produce uniform effect all to the depth. Now, you will not consider the submerged parts. So the submerged parts from this point will have effect on the what? On the retaining wall, increasing with respect to depth because water is all through from that point all to the bottom. I don't know if you get that. This is not actually a core content of the That's clear. All right, fantastic. Yeah. All right. Now moving on. All right, I think I've said some jargon. So, summarily, everything I've just tried to prove is that always be conscious of the fact that we generate active earth pressure and we can generate passive earth pressure. For retaining wall, what we are concerned about when we are designing retaining wall is active earth pressure. But for our sheet pile design, we are concerned about both passive earth pressure and active earth pressure. And we derive the formula that what for your active earth pressure, it is what? Ka times unit weight times your depth. Why for your passive is what? Your passive pressure is what? Kp times what? Times your unit weight times your what? Your depth. Where your K is what? Coefficient of active earth pressure, and your Kp is what? Your coefficient of what? Of passive earth pressure. Now, we established that scenario, and I brought your attention that you need to also understand that even though the man gave us a scenario of an earth material, all right, an earth material, and it also gave us another scenario of a surcharge acting. So that compelled me to actually also dive a bit into when you have a surcharge acting and you also have what? An earth material acting. Now, you can calculate your pressure of your what? Your earth material, which is K alpha Z. But for your surcharge load, it is uniform. Just multiply that your surcharge uniform load by your K. It's going to give you what? It's going to give you what? The lateral earth pressure. And that lateral earth pressure is going to be the same all through the depth. And that is why it is rectangular in section and not triangular in section. So you need to take note of that formula that one is what? KAQ. And your active earth pressure due to your S dam is what? Is triangular. That is what? KAQ-ish. So by the time you are taking your area for your surcharge will just be your normal area of rectangle, which is length times square. That is KAQ times H. While your area for your S dam is going to be half KA alpha H times H squared. That is your area of what? Your area of triangle. It's going to get clear as one starts solving. So let's just move quickly to the theoretical background of retaining wall because of what we did tomorrow. So we have basically 4 types of, let's say 5 types of retaining wall. We have the graffiti retaining wall. Now, graffiti retaining wall is that there are some retaining wall that we don't use reinforcement. Like you just make sure that it is extremely heavy. Like you make sure that your concrete is extremely heavy, your concrete mix is extremely, heavy too. So it's the weight of the concrete that will actually be what? Be preventing what? Be ensuring the stability of what? Of the retaining wall. So in that case, we don't do reinforcement. So that is not basically a core content of the course. And if you can see now, you can't see any reinforcement in this. So this is it's always very large, although very large, but then the height is always limited. And so it's not economical height. Semi-graffiti retaining wall. Now, to reduce the size of a graffiti retaining wall, because like I said earlier, for your graffiti retaining wall, it's basically concrete all through. Now, to reduce the size, we have semi-graffiti that will introduce little reinforcement, small amount of reinforcement inside it, so that at least reinforcement will be doing some job. So that one is basically provided, and it makes it a bit, as not as gigantic as your graffiti retaining wall. Now, moving on, this is the most important aspect. This is what we are designing in this class. The cantilever retaining wall. It's often the most common type. Now, this is basically made of reinforced concrete. There's nothing like your reinforcement is small. There's nothing like your reinforcement is not small. Now, this consists of a thin stem and a base slab cast monolithically. Now, I'm not using English. This is the way it is used in our notes. So, monolithically means that when you are doing your form work, all right, if you are doing your form work on site, there are some shape that you will construct it. Not that you first do the base first of the shape, you will not cast the base, then you do the height first, you will not join. No, you do the form work in a way whereby the form work will be done together and you are going to cast all of them together, and that's where the word monolithically is coming on. And it's very economical because we are using enforcement. So this is basically what we're trying to say. Now, this is the cantilever aspect, which is always called the eel. We are going to see the detailing very soon. Now, this is this vertical stem. Don't forget that they are joined their own trapezoidal section. When we are solving, we basically represent our own with what? With a rectangular section. It's dependent on what we are solving. So, and the other aspect is just counterfort. Counterfort is, I don't think it's part of the scope of this type of for OBJ purpose. Counterfort retaining wall. Basically, what that one do is that they have something in between called counterfort. That thing is also adding, is also supporting the retaining wall. So let's say this is your retaining wall now. So in between your base, in between your base and the vertical stem of the retaining wall, they are going to have probably an additional support. At the other side, your backfill is this is where your backfill is, obviously. So you are going to have it at that side of your backfill, and it's going to be acting for support. I don't think this is important though, but it's crucial we mention it since I think it's insurance good or thereabout. So let's get to it. All right, I think before I continue, please, if you are not following it before, try to follow now because this is basically what we are the main purpose of this class. Or if you have any problem, am I too fast? Should I reduce my pace for this particular aspect so that I can know everyone is on pace? Hello? Can you hear me?
Yeah, hi Taiwo, how are you doing? So thank you. So you can actually, since like you said, this is the most important aspect. So I would like you to just take it slowly. Some people might want to jot things down. So it's just kind of take it slowly. All
right. I also need to state, thank you so much for that. I need to state that jotting should not be a priority because I think the slide that I have is quite detailed. So you can always have access to the slide later. But if you want to take anything I said, you can always jot that down. So I'll try to be as slow as possible. Now let's start. I have a diagram here. Obviously, we are considering a cantilever retaining wall. Now, the diagram I have here is basically, this is my backfill. Now, this inclined aspect, where my mouse is hovering, is basically my back view. Apologies. Where my mouse is hovering is basically my back view. Now, this is the retaining wall. Obviously, because my back view is here, this is, let's say this is they've taken the resultant of your active earth pressure, and that resultant will be acting at what? At h/3 from base of the what? Of the triangle. Don't forget that your pressure distribution of what? Of the active pressure is triangular, and that's why it's what? h/3. So I know that this is acting here. Now, because this back view that is acting on this retaining wall is going to be acting here. And don't forget that this retaining wall itself also have weight. This retaining wall also have its own weight, acting vertically downward. It's crucial to state that, like I said, I think I mentioned in the class that based on our experience, that line of action of force is continuous to infinity. So I can extend it as much as I want. So I'm extending this lateral edge pressure, which is horizontal. Don't forget your lateral pressure is horizontal pressure. Now I'm extending it to meet the vertical weight of the retaining wall itself. Now, as it's meeting the vertical weight of this retaining wall, they're going to meet at a point. Now I can extend this out. If I extend this particular thing, don't forget the arrow keeps on going. So I can keep extending. From your knowledge of resultant, it's very clear that the resultant effect of your lateral pressure and your weight is going to go along this direction. It's going to go. Just follow me. This may seem very, very unreasonable now, but it's very important. It will make you a proper understanding of our design. Now, your resultants, these your resultants coming vertically downward. That is, obviously, you have this going like this. If you remember your Cartesian coordinate of normal resolution of forces, I know some people must have seen it. Was there as it's coming like this, and I have my weight, I know my resultant will be coming like this. Now, my resultant will be acting at this particular point on the base, that is the base of my what? Of my retaining wall. Now, that particular point, I call it space B. Now, also, because this is acting on this particular what, or the resultant effect of the applied forces due to the lateral edge pressure and the vertical weight is acting on this point. For this thing to actually stay, there must be a counteracting what? A counteracting force, a counteracting reaction that must make this thing. Now, this counteracting reaction, I call it R prime. The resultant effect of the what? Of the weights, I call it R. So both of them will counter each other, and that's why you see that the arrow are facing each other opposites. Now, also, fully aware, I can also resolve this one to my what? My vertical reaction and my horizontal reaction. So basically, what I want to know is that you can resolve your weights to the vertical and horizontal aspect. Your weight and your lateral edge pressure is given in the vertical and horizontal aspect. Your lateral edge pressure is the horizontal, your weight is the what? Is the vertical. Now you can generate a resultant of that. Generating a resultant of that will help us resolve our what? Our reaction into what? Into vertical reaction and what? Horizontal reaction. And this is the particular point. Let's move on. Now, for the equilibrium of that particular place, I can now say that what? My vertical reaction is equal to my W, which is the weight, obviously, and weight is acting vertically downward. And my horizontal reaction of what? My PA, because it's not acting towards this other direction, while my P is acting towards the other. All right. Now, obviously, the third equation, namely, that is, we've used our vertical, we've used our upward forces equal to our downward forces. Now we actually use, and we've also used our what? Horizontal forces, left-hand forces equal to right-hand forces. The other side is what? The other condition of equilibrium is what? Is to take moments. Now, why we are taking moments is that it is crucial for us to know the concept of eccentricity in retaining wall, because we are going to use it in our design too. Now, if we take moment about point C, this point C, center of the wall. Now, if you take moment RV and what? You are taking RH will not take moment because the line of action is going to call that is 0. RV will take moment about that point. That will be RV times what? And you are taking moment about point. I think we are taking moment about the toe. Yes, about the toe. That will be what? RV times X. All right. Then obviously equal to, because this is going to be causing anti-clockwise, then equal to your weight will also take moment. Your weight to be equal to that will be weight times A. Look at towards the toe. This is the toe. So I've indicated that dimension. And you also take your minus your P. Your P also is going to be what? Opposite the width. So your P is also taking and you can take moment at your toe. Why the distance for your P will not be what? H/3. Don't forget moment is perpendicular. So even though, so you are not going to be using this, your P is acting like this. You are going to take your perpendicular distance, as we all know it. So one thing you just have to understand that this will help you just understand that you can take moment of what? Of PA, you can take moment of your weight, you can take moment of your reaction in the course of your design. So just probably have this as at the back of your mind, which we are going to do subsequently. Now we also need to know that we need to generate eccentricity, and eccentricity is just basically what? The distance of the center of the what? Of the retaining wall to the point of the reaction, that is where the reaction is occurring, that is where your vertical reaction, because this may be a likely object question. You may ask, okay, what is eccentricity? You need to know that what eccentricity is basically the distance from the center of the wall to the vertical what? To the vertical, the resultant vertical reaction of what? Of your retaining wall. The man may put it in any way, but it's crucial for us to actually know that. Now, for a safe design, the following must be satisfied. First, no sliding. Now, the wall must be safe against sliding. In other words, what we're trying to say is that when we are talking about no sliding, you need to know that what actually causes sliding on your retaining wall is your horizontal component. And for you to know that your horizontal component is mostly responsible for sliding, your resultant vertical forces acting on that particular retaining wall must be greater than your what? Than your horizontal what? Your horizontal distance. So at that particular moment, you know your factor of safety is your total vertical force multiplied by the coefficient of friction over RH. You have to have this at the back of your mind. Very important. When we are solving, we are going to understand it. And don't forget that your coefficient of friction may be given in terms of what? Angle of internal friction. Now, if you are giving in terms of angle of internal friction, you take your time to get your what? Your coefficient of internal friction. Now, the second condition, the first condition is no sliding. The second condition is that the wall must be safe against overturning about toe. Now, let me go back. Basically, you have your toe. This is your toe. Now, this is your toe here. So, overturning here must be presented. If this thing is turning around, this obviously is going to cause what? It's going to cause failure. And then, so for us to prevent overturning, what basically causes overturning? From your knowledge of slope stability that Shemun taught, you know, we have our overturning moments and we have our what? Our resisting moments. I need to emphatically tell you that what? One thing is only responsible for your overturning moment, and that's your horizontal forces. So, in a particular scenario whereby you only have what? Your X dam acting on it. If you only have your X dam acting on it, once you take the horizontal, once you find the lateral exposure, that is Ka alpha H, that is what will be causing what? Just take that one, find the resultant force, then take the moment about the toe. The moment about the toe will be times H over 3. We are going to see diagrammatically soon. So what will be responsible for your overturning moment alone for OBJ purpose? Please note, it's only your horizontal component force that are responsible for your overturning moment. Now, although if you have your surcharge load, don't forget that your surcharge load too will also have its own what? Its own lateral pressure. It's also horizontal. In that particular phase now, you are going to be having your active earth pressure that is from the soil itself, and you're going to be having the active lateral pressure from what? From the surcharge, because the surcharge load will also cause what? Horizontal, like we explained earlier, which was a rectangular in section. But for your resisting moment, what will be resisting moment about two? Basically, since horizontal is causing what? Overturning. When you take your movement of what? Of all your vertical forces, that is, your weight is acting vertically downward, the weight of your stem, the weight of your base, of your heel, all of those will be what we're acting as what? As resisting moments. So note that vertical forces cause resisting moments, while what? Horizontal forces cause what? Overturning moments. And the factor of safety is always between what? 1.5 to 2.0. You have to know this by heart, and it is written in the slide, or your notes can always go back to that. Now, the third condition is no bearing capacity failure. I must state that this is, like, to me particularly when I was reading the mass notes, this place was quite confusing in the course of design. So one thing you just have to know that for you to generate or for you to know your bearing capacity failure, now you'll be given the maximum bearing capacity of the soil. Right? Now, it's not your job to now calculate, you've given the maximum bearing capacity that the soil can withstand. Now, it's not your job to now calculate the maximum pressure acting at the base of your retaining wall. Once you can get your maximum pressure acting at the base of your retaining wall, then you can easily get your factor of safety. And from the formula for calculating your maximum pressure is this. I'll make it, you don't need to cram this. By the time we get to solving, I'll tell you the best approach to actually go about it. You have your horizontal reaction over B1 plus 6E, where E is your eccentricity, which I said eccentricity is the distance between your vertical reaction and your center of the wall. Now, your QMA is the allowable bearing pressure, which should be given in the question. While your P mass is what you have to look for yourself. So you are going to probably get your pressure distribution by the time we start solving now, and then you get your maximum pressure. Once your maximum pressure, your allowable pressure must be greater than your what? Your maximum pressure. The maximum pressure acting on the base must never exceed it. And for factor of safety, they say 3 is usually specified, provided settlement is within allowable. And the last one is what? No tension. No tension. There should not be any tension at the base of the wall. So by the time remember, I'm also going back to eccentricity. Eccentricity is what? Eccentricity is the distance between your what? The center of your wall between the center of your wall to the point of action of the what? Of the vertical reaction. The point of action of the vertical reaction. You need to know how to generate your E. Once you can get your E when your E is greater than B over 6, what is your B? Your B is your base width. When your E is greater than B over 6, tension crack may develop at the E, or certainly develop. So just look at the issue, the tension scenario as when we design, what we are used to design and say K is less than 0.156. So this is part of those design code specifications that if your E is greater than B over 6, you must cater for tension. I think the example in class, the man did not actually, the one he gave us, an eccentricity was not greater than that. So hopefully, but let's say in exam now, when you are solving and your E is not greater than your B over 6, I really I've not seen how they actually, try to probably calculate that. Okay, let me see what is written here. This tensile strength of the soil is small and tensile, okay. So just test that me, if I see that tension develops, I'll probably just, scam the man and say that, okay, since this is greater than this B over 6, obviously tension will develop at the surface, and which is going to reduce the effective base area. So for me to now increase the effective base area, you can now say increase the dimension of your base, and that should be all. That should take care of it. When we get to design, I think that should become clearer. All right, great. Analysis and design of retaining wall. So there are various stages involved in the analysis and design of retaining wall. Your calculation of lateral pressures, which I've given a brief review on, and then your assumption of the width. Mostly when you design, obviously on site, as an engineer, you start by assuming that, okay, let me start with this. But majorly, the man actually gave us dimension. Maybe he believes we are still novice, so he gave us dimension so we are not for the man, but we are not actually basically assuming. Okay, so he gave us what to use to put up our geometric dimension of the retaining wall. But real life scenario, you have to probably assume. And then calculation of your base pressure, which I said that there was a formula I gave for calculating maximum P mass or so, which I said you don't need to count that. When we get to solving, you are going to see the better approach. You calculate your bending moment. Obviously, whenever you want to design, we are designing to resist what? Effect of shear forces, bending moment. And then we calculate the shear forces also. And we determine the thickness and reinforcement that can actually provide resistance to the bending moment and shear forces. So sample design exercise. And obviously, and thanks to Shion, I was able to get this from his notes. And then, so let's get to it. So what we have here now, we have a retaining wall section given. Now, the demand said they gave us allowable soil bearing pressure, which is 120 kilonewton per meter square. And this should bring to your mind that, okay, this allowable soil bearing pressure will assist you in checking for your bearing capacity failure. You are giving angle of internal resistance, you are giving coefficient of friction, you are giving your unit weight of soil, you are giving your surcharge. Fantastic. Now, so apart from the fact that you are having a soil here, where my mass is hovering, now I need to also state that your retaining wall, when you draw a retaining wall like this particular vertical aspect is called the vertical stem wall. It's called the vertical stem wall. This particular side, this horizontal, is called the base, but this base is not divided into two parts. The smaller part of the base, so you don't always think that, I think some people make the mistake of your toe always be towards the left. No, the smallest part of your base is the toe, while the larger part of your base is the heel. Now, your back heel always rests on your heel. It's crucial to note that your back heel always, so even though the question or the man purposely did not indicate that a soil is acting here, it is expected of it to know what you cannot have a retaining wall if you are not retaining anything. So the material you are retaining is obviously here. Now, how will you now know whether it's soil or not? Come to your question. You are giving unit weight of soil to be what? They never mention anything like submerging water. The reason that they are added is that apart from the fact that there's a soil here that will be causing a lateral pressure on this retaining wall, you also have a surcharge acting on it. Now, thanks to Sheon, he detailed this by saying that, okay, don't forget that your soil will be causing, as you are going down, increasing your depth, the pressure, the lateral pressure caused by your soil will keep on increasing, which makes it very low, and that is why it keeps on increasing. That is why it's triangular in section, and it will be acting at what? Point what? H/3 from the base, and from this point is what? 2H/3 from an edge of century. Now, you need to know that there's also a surcharge there, and she also indicated based on what we have here in his notes that what we have this, all right, which is rectangular section. Why? Because it is uniform, irrespective of your depth of the depth of your retaining wall. Once you calculate 5 times this, let's say this is 5 times any particular, when you take the area, by the time we get it, you convert this one first to your units and to your pressure. How do you convert your surcharge to your pressure? And I think I specifically state that for you to convert your surcharge to your pressure, your P is Q times Ka. Your P is Q times Ka for you to convert. Why? For you to convert your soil to pressure is Ka times unit width times height. Ka times unit weight times height will be used to convert your soil into your lateral height pressure. But when you are converting your surcharge load into pressure, it's basically what KAQ. And that will just be, you can calculate your Ka from Rankine. We developed that Ka is what? 1 minus sine phi over 1 plus what? Sine phi. And they're giving us phi in the question. Phi is our what? Is our angle of internal resistance. We guess that one as we move on. So that is basically, so the explanation of this diagram is shown notes. I really hope it's clear based on what I've explained now. So let's move on. Now, when you want to design a retaining wall, you have to think of 4 things. The first safety criteria should come to your mind. No sliding, no overturning, no bearing capacity failure, no tension. Those are the 4 things, and you must ascertain that those four conditions are met before you can say, yes, this retaining wall is safe. So we are starting with what? With our stability analysis, that is our sliding, that is no sliding. Now, how do you, before you can even calculate your sliding or provide your overturning moment, it is crucial for you to convert your soil into what? Lateral earth pressure. Don't forget that for retaining wall, we only consider the active earth pressure. For retaining wall, we only consider the active earth pressure. But for sheet pipe, we consider both what? Both active and passive earth pressure. Now, for this retaining wall now, we have PA equal to what? Ka alpha times H. Now, how do you calculate your Ka? We derive it from Rankine. Is 1 minus sine phi over 1 plus sine phi. And that is why we have 1 minus sine 35 over 1 plus 35 times your unit weight is given in the question. And that's why I specifically, all through the solution, you'll be seeing the question beside. So you can easily refer to it. You have your unit weight to begin as 18, and that's why it's 18. And your height, what's the total height of the retaining wall? 5.5 plus 0.5. That will give you what? 6. And that was why I was able to get the maximum. So automatically, I know that the maximum possible, the maximum lateral height pressure possible on this retaining wall is this particular place where my mass is hovering, and that is what? 29.27 kilonewton per meter square. Now, from the pressure distribution, we can get our resultants. How do you get your resultants? You take the area of the triangle. If I take the area of the triangle, obviously that will be what? Half base times height. I've gotten my base radius to be what? To be 29 points. I've gotten my base to be 29.27. I know it's half. Then my height, what's the height of the what? Of the triangle is 6. So I've gotten my what? My earth force. So this my earth force is what? 87.81 kilonewton per unit length. And also, don't let the per unit length confuse you. It's just, you have to understand that whenever we are designing in civil engineering, all our design is always what? Per unit, per meter length per this. So what that simply signifies is that this is the amount of reinforcements that can cater for a meter length. And that is why you see that we always have per unit length. Because I was expecting, if you are curious enough, you may want to ask some. Obviously, a lot of people should know this though. But I need to also ascertain that if this is really unit weight, if this is really UDL, uniformly distributed load, it's supposed to be what? 5 kilonewton per meter. From our knowledge of bending moment on beam, our knowledge of bending moment on beam is always what? 5 kilonewton per meter. But we are putting per meter square because this UDL is not a UDL for the entire retaining wall. It's only a UDL for 1 meter of the retaining wall. So it's 5. So what this implies is that what? Q is acting, the value of Q is 5 kilonewton per meter length. So for every 1 meter length, the UDL is what? 5 kilonewton per meter. So that is just basically a side notation. Now, coming back, we got our what? Our force, which is what? PA equal to what? 0.5 times PA times H, and we derive that from our area of triangle. Obviously, the next thing that should come to your mind is that we need to also get what? The lateral height pressure for our surcharge. And I believe that should be the next thing in my slide. All right, so we have to consider the surcharge. Now, your surcharge, like I say, your surcharge obviously is what? Is same thing, KAQ times KAQ times H, because you have to understand that why I think when I started, I said that it is KAQ without putting H, but I specifically emphasize that your surcharge is independent of your height. That is, it's going to be the same all through. Your surcharge is going to be the same all through. So the maximum possible there is just when you check your total height, that will be total surcharge. Unlike your active earth pressure, where you have Z and not H in the formula. Z means that at this particular point, your pressure will be different from this particular point. But for your surcharge, your formula is just substitute what? Your unit weight. Our active earth pressure is Ka alpha H. So change your unit weight, change it to Q. If you change it to Q, your Q is given in question as 5. We've gotten K as what? 1 minus sine 35 over 1 plus 35, then times 5 times 6. Then you got what? 8.13 kilonewton. You may want to put per meter length or not. But Sean decided to probably remove that. So your total lateral load now, based on the problem we did earlier, will be the combination of what? Your active earth pressure from the what? From the soil, and your what? Your lateral earth pressure from the what? From the surcharge. By the time we add both of them together, we are going to get what? 95.94. So these are what? Don't forget lateral. Lateral is basically horizontal. So we've gotten all of this. Now let's now go to our design criteria. The first design criteria is what? Okay, before we go there, I think Sheon calculated vertical forces, because I think it's trying to do everything one by one. You are going to be needing your what? Your horizontal forces. You're going to be needing your what? Your vertical forces at the long run. So for your vertical forces now, you will not take them components by components. And that was why I explained that you need to understand that you have your weight and you have your base. Now, your base can be what? Divided into two, your toe and your heel. But then, when you're calculating the effect of force, you take a base as a whole. The only time you consider your toe and your what and your heel separately is in the course of reinforcement provision, which you are going to get. But when you want to calculate your vertical forces, now this is your wall. This is your vertical stem wall. So we can easily calculate our vertical stem wall. Now, the calculation of our vertical stem wall is area times unit weight. From our knowledge of design, once you get your area, multiply by the unit weight. And unit weight of concrete should be 24 kilonewtons per meter cube. By the time you multiply by area, you are going to get your what? The force, the vertical force caused by this what? By the effect of the weight of this particular, and it's going to be acting at the center, obviously, because this is a uniform is value, so it's going to be acting at the center. Obviously, for your base 2, your length of your base is 4.5. So the area of your base is 4.5 times 0.5 times 24, which is your unit weight. So area times unit weight of your base 2 will give you your what? Your force, and that is 54. That 54 will also be acting at the center of your base. And the center of your base, 4.5 divided by 2, that should be 2.25. So that I think you just need to take note of that. Why for your wall is acting at what? 0.2 center, and that's also what? Area times what? Unit weight. And also, that is not basically all this stuff causing vertical. Your earth also will have effect on vertical. For your earth, you are going to get your that your earth will consider what will basically prove that took quite a number of time was being aware that for you to calculate your lateral earth pressure from your what? From your earth and from your surcharge, you are going to make use of KA, KAQH, KA alpha H. But when you're calculating the horizontal effect of your what? Of the earth soil, is basically your unit weight of your soil times your area. That's all we are using. Area times unit weight. So how will you not get the area of your earth? The area of your earth is very clear here. That's why I said that you need to note. I think I said it earlier that your soil will always act on top of your heel. It is not going to act on your toe. So how will you not get the area of your soil? The area of your soil is just basically the height up to the base. This is 5.5 times the length of your heel. And length of your heel is what? 3.1. So 5.5 times 3.1 will give you the what? The area of what? Of the soil, of the earth material in this particular region. So you have to multiply that by your what? By the unit weight of what? Of the earth material, which is given as what? 18. Don't forget your earth material is not concrete, so we can't use 24. They gave us a question as what? 18. When you multiply, you get your earth vertical force. And also your surcharge. Your surcharge is just what? Because this is obviously your surcharge. Now we are considering the vertical effect. Now when you are considering the horizontal effect, I think also knows that when you are considering the horizontal effect, the H we use our height. Or when you are considering the vertical effect, the H you use is going to be your horizontal length. So look at this 5 now. The length of this 5 is what? 3.1. By the time I multiply what? My 5 times what? 3.1 is going to give me what? The vertical effect of what? Of this surcharge, which is what? 15.5 kilonewton. Moving on. Note that the unit weight of concrete was taken as 24 kilonewton per meter cube in the competitions. I think I said that. And then design criteria. So let's now move to the 4 basic design criteria. You have your no sliding is the first one. No sliding, of course, from the proving I showed you guys earlier is what? Is always your coefficient of friction times your total vertical forces over your total horizontal forces. Now all you have to do is that what? We've gotten our total what? Vertical forces. That is addition of what? Of all the vertical forces. Let me go back again. What makes your vertical force? 4 things make your vertical force. 1 is your wall, this vertical wall. The second one is this horizontal base. The third one is what? Is the soil itself. It's going to cause vertical force. While the first one is the surcharge. It's also going to cause vertical force. So those are the 4 things that make your vertical forces. But what makes your horizontal forces are just 2. Only 2 things make your horizontal forces. And those 2 things are just your what? Your soil and your surcharge. Please take note of that. Now, we've gotten our vertical force. That is why if you go back, you see that now our lateral force, we only have our PA plus PS, that is our active earth pressure due to the what? To the earth material and the surcharge. But for vertical, we are going to have addition of these 4, wall plus base plus earth plus surcharge. And that was how we were able to calculate our total vertical. So total vertical is the 4 of them. We got 429.2 kilonewton. Now you have to go back to your sliding what? Sliding is what? Total vertical forces over total horizontal. But that total vertical forces you have to multiply by your what? Your coefficient of friction, which is given as 0.5. You've gotten your total vertical force all over what? Your total horizontal. So you get 2.24, which is greater than what? 1.6. So I think the man is using 1.6 or so. I think everything in the slide and is in the notes. You can always check that for OBJ purposes. Now the next criteria is now no overturning. Now, from our knowledge of stability of slope, which I also explained earlier, that what overturning moment are caused by what? Horizontal forces. In this case, we only have 2 horizontal forces: our active earth pressure and our surcharge load generates the overturning moment about toe. Overturning moment about toe. It is crucial because that is really going to direct how you take your movement. Now, all we just have to do is that, since we know that what? So horizontal forces are responsible for what? For overturning moment. So let's take moment of these horizontal forces. Now, how can you take moment? You can only take moment by being strategic with your what? With your resultant force. I know that the area of my what? Of my X is 5.5 times what? Times 3.1. That is this particular place. Now, because this also is uniform in section, right? It's uniform. So the resultant, if I want to convert that uniform earth material load to what? To a point load, it's going to be acting at the center of this particular, that is for vertical. Also, but for your horizontal, we've gotten our horizontal to be what? From our triangular, for the effect of the horizontal force, it's going to be acting at what? H/3 from the base of the what? Of the triangle. H/3, and the total height of the triangle is what? Is 6. So 6/3. So if I'm taking the resultant moment, don't forget, only horizontal forces. Only horizontal forces cause overturning moments. So the first horizontal force I'm going to take is this PA. Now, the resultant PA is acting at H/3 from the toe. This is the toe. So the distance between this and this is H/3 from our centroid. That's why we have 6/3 as well, 7.1. Now, for our surcharge, obviously, our surcharge is uniform, obviously. So it's going to be acting at what? H/2. That is at the midpoint of what? Of your 6. That's why you have 6/2. By the time you have both of them together, that's your total overturning moment. Now, the next thing is now to calculate your resisting moment. Your resisting moment are caused by what? Vertical forces. That is your S load, your weight of wall and base all contribute to the what? To the resisting moment to counteract the what? The overturning moment. Now, taking that, we can easily say that, okay, our wall. Now, you have to be very careful now. You've calculated your vertical forces each. So, we've gotten the vertical force of our what? Of our wall. And I said that what? The vertical force of our wall we got is going to be acting at the center. That is 0.2 of this wall. So, if you are taking moment about this point, 1.0 plus 0.2, you're going to get what? 52.8 times 1.2. For your base is this total base. This total base is here. Now, we got it as 54. The total length of the base is 4.5. It's going to be acting as what? As the center, which is what? 2.25. That 2.25 should be around here. That 0.5 should be around here. So for you to get your total this thing, your total length will now be from here up to what? Up to the center, which is what? 2.25. So let's say that we have 2.25 is acting, your base is acting 2.25 at the what? And that will just be your distance. Apologies for the mishaps. So you have your base, right? So what your base load is 54 towards the center is 2.25. So we take moment. For your earth, exactly, this was what I was trying to explain earlier. For your earth, you have your earth vertical force. When you convert to vertical force, don't forget we're only using the vertical component of all this. Obviously, your work cannot even cause horizontal components. Your base does not have horizontal components. But don't forget that your earth and surcharge has horizontal components. And we consider that in overturning moments. But for vertical moments now, for resisting moments, we are considering the vertical what? The vertical effect, that is the weight of the what? Of the earth itself. And which we calculated earlier, we got 306.9 times. Now, the weight will be acting at the center of this 3.1, because this is where your earth is actually feeling, which is 1.55. So if this place is 1.55, 1.55 plus 0.4 plus 1.0. So you can easily say 1.55 plus 1.4. That will give you 2.95. Same thing goes for your surcharge. Your surcharge is also acting at the what? At the center, that is 1.55. And you take moment, that's your total what? Resisting moment, which is what? 1135.95. Now, moving on, we have hence our factor of safety will just be what? Resisting moment over what? Over overturning moment, which must be greater than what? 2.0. And this is 5.68. Now, personally, I think this is the most confusing in the design of the retaining wall. So I'll try to take this slowly. Factor of safety against bearing capacity failure. Now, we are given our allowable soil bearing pressure, which is what? 120 kilonewton per meter square. Your main aim for you to check against bearing capacity failure is to get the P mass, which is your maximum what? Your maximum base pressure. Once we can get our maximum pressure and ascertain that it is lesser than what our allowable soil bearing pressure, then I think we are good to go. So, but the problem is, how can you generate your P mass? You have to understand that your P mass also have pressure distribution. Look at, you are going like this is the total, this is your base, right? This is your base. Now, this particular point, this outer part of the E, I said from here to here is E, from here to here is always having what? The minimum pressure. Because as you are moving towards your toe, the effect of the pressure towards the base will be increasing. And that's why we have a stress distribution at the base. That is, your P minimum will be here and your P maximum will be here. Now, why this is very important for us to actually note is that when we are designing, because we've not started designing, we are still checking design criteria. It's until we met our design criteria, we'll not start designing for their movement, for their respective movement. But you need to understand that when we are designing, you will design your heel separately, you will design your toe separately, you design your what separately. And it's going to get extremely complicated if we did not take note of the fact that your pressure at the base increases from your heel to your toe. So as you are going, the pressure here is different from the pressure here, just the normal way for that right pressure that's acting that way. So please take note of that. To begin with, let's reduce the base pressure. Now, that formula that I said is RV, open bracket, something. So you don't need to calm that, all right? What you just have to know is that what? Your base pressure is what? P equal to what? W over B divided by B plus or minus 6M over what? B squared. Now, where your W is your total vertical forces, your B is your base width, your M is movement about the base center. You need to know that when you are calculating your base pressure, we take moment about the base center. But for overturning moments, we take moment about the toe. Those are the nuances of the design that you have to take note. Now, you take moment about your base center for your when you're calculating your base pressure. But for your overturning moment is what? About the toe. Please take note of that. Now, I think Sean is taking anti-clockwise moment as positive from what I said in this book. Now, let's now start. Also, I need to lay emphasis on this plus or minus. The reason why this formula is having plus or minus is that automatically, when you use plus will give you your maximum base pressure, which is the pressure here at this particular point where my mass is hovering. When you use minus, it will give you your what? Your minimum, which is the pressure at the beginning of your what? Your E. While your maximum is the pressure at what? At the beginning of your, at the end of your toe, rather. So let's not take moments of the what? Let's not take moments about the base center. That is, we're basically taking moment about the, let's not start each condition. This 87.81, 87.81 times 2 times this thing. 87.81 is gotten from. So 87.81 is for apologies. Let's be sure. 87.81. I think that'll be my lateral height pressure. Okay, good. So that's my lateral, my horizontal force that is acting at H over 3. All right, fantastic. So let's just quickly, be conscious of those forces. We have two lateral height pressure. The second one is what? 8.13. That one is acting, all right? And then we have, the next one is we have our vertical forces, the wall, the base, the earth also have vertical force and the surcharge, respectively. So we'll be making use of their values now as we are going on. Now, so let's take a moment. So the first thing is that your 87.801 is your horizontal what? Your PA. Your PA, and your PA is acting. You are taking moment about the base center. Even when you are taking moment about the base center, in this particular place now, this is horizontal force. So the distance you have to use is your vertical distance. You can't use your horizontal distance, obviously. So this is so the distance between your base is what? H over 3 from our center. That's why we have what? We have 6 over 3, and that's why we have 2 there. 6 over 3 will give us 2 because the total height is 6 plus obviously also have its own horizontal. From the surcharge horizontal, we have that will be horizontal is acting at the center at the midpoint of the what of this. That will be 6 over 2. That's why we have 3 plus our 52.8. Our 52.8 I think should be for 52.8 is the, I should have written this thing down beside this place. 52.8 should be one of our vertical forces. I think we can easily deduct that, and I think that should be our vertical wall. Our vertical wall Well, yes, our vertical wall is 52.8. So the weight of our vertical wall now is 52.8. Now you have to be careful of your base. You are taking moment about the base center here, and your vertical is acting here. So the distance is that, don't forget that your base center is 2.25. So if your base center is 2.25, and you already have from here to here to be 1.2. So for you to get the distance between that center and the base center is going to be 2.25 minus 1.2. I really hope you get that. If you did not get that, please signify so I can probably explain with diagram. Then your 306.9 is your vertical force of your what? Of your earth. So basically, what you are using to take, you are using both your horizontal component and you're using you're also using your what? Your vertical component to calculate your movement. But do not be mistake of using your vertical components of your how would I put it? You are only using the vertical component and your horizontal component of. Sorry, I need to confirm something. Okay, you're not using your base. You are not using your base. What you are using here is 87.801. This is your first lateral height pressure. This second one is your what? 8.13. This is the second one, which is your what? Your lateral height pressure. This is your surcharge. Now, this one is the vertical. This vertical wall, this vertical stem, which we've done that, and we take the second one is now what? The vertical force of. Don't forget that we've taken the what? The horizontal aspect of our S down, which is this 87.81 that gave us lateral height pressure. Now, the vertical aspect too will also take what? Will also take moments, and we got what? 306.9 to be the what? The vertical force of our soil times the vertical is acting at this particular point also. Is acting at this particular point, which is supposed to be 1.55 if I'm not mistaken. So you have 1.55 here. You know, this is acting at 1.55 because your total length is 3.1. So if it's acting at the center, it's going to be what? 1.55. So if it's acting 1.55, so 1.55 plus your 1.4 will give you what? 2.95. And that's why you say, okay, you have 2.95 minus your what? Your minus your 2.25 because you are taking the distance between what? The both of them. This will become clear with diagram if you are taking moments. I really hope. Are you guys with me?
Hi, Taiwo. Yes. Can you come again for this moment stuff?
All right, fantastic. Yeah. While creating this slide, I should have made this more. Okay, let's see. Let's start. So, you know, I want to take my moments about the base center. So I'm going to take moments of all force components about the base center. Now, note that your wall is going to have what? A vertical component. Abi, your earth itself, that is your earth material, is having two components, both horizontal and vertical. And those two will take what? We are going to take their moments about their base center. Your surcharge too. You are going to take your surcharge about what? About your surcharge will also have two effects, your vertical and your horizontal. And the only one that you will not take moments is your base, because the base itself, you know, when you take the result of your base, the base load will be acting at the center, and you are taking moment about the base center, so that will give you automatically 0. There's no distance between them. So where the challenge is now is you getting the appropriate distance between the resultants of each component you are taking and the base center. So I started with the what? With the horizontal component of the what? Of the soil. The horizontal component of the soil is our lateral height portion, which is what? 87.8. And it's going to act at what? H/3 from what? From the base. Why we are using H/3 is because it's a horizontal force. So if we are taking moment about the base, we have to use the perpendicular vertical distance, which is H/3, and that is 6/3. We got 2. For my 8.13, my 8.13 times 3, that is the horizontal component of my surcharge. And the horizontal component of my surcharge is at the midpoint of the retaining wall. And the total height of the retaining wall is 6. So 6 over what? Over 2 will give us what? Will give us 3. Plus 52.8. I said 52.8 is the weight. The 2.8 is the weight of this vertical stem wall. Now, the resultant of this vertical stem wall will be acting at the midpoint of this wall, which is 0.2 at 0.2. So 0.2 plus 1.0 will give you what? 1.2 from the toe. So this is 1.0 plus. So you can say that what? The weight is acting at 1.2 from the what? From this particular toe. So, and you are taking moments about this point, right? You are taking moments about this point. So for you to know the distance between, the force is acting at the center here. So you need to know the distance between here and here. You need to know the distance between this center and this base. So for you to do that, if you know that from here to here is 1.2, and from the beginning also to that center is what? Is 2.25. From the beginning to that center is 2.25. And from the beginning to the center of the wall is 1.2. So for you to know the remaining distance that is left, you just have to subtract them. That's why we have what? 0.25 minus what? 1.2. Then the next one is now what? Don't forget we've taken the horizontal component of our We've taken the horizontal component of our earth material. Now let's not take the vertical component of our earth material, which is 306.9. Now 306.9 is the, and we generated that by using what? Area multiplied by unit weight earlier. So we got 306.9 times. So the 306.9, don't forget, this is where your soil is acting. Because your soil is acting here, your vertical weight of that soil will be at the center of 3.1. I mentioned emphatically that what? Your soil will always be acting on your heel. And the distance of my heel is what? 3.1. So the center is what? 1.55, right? So if the center is what? Is 1.55, right? So I need to now calculate the distance between this the weight of this particular what? Of this particular 306.9 and the base center. Now let's now start. The center here is from year to year is 1.55. But don't forget that what? From year to year 2 is 1.4. From here up to this particular ending of, from here like this is 1.0, then the wall itself is 0.4. So up to the ending of the wall before the heel starts is what? 1.4. And don't forget that your earth itself is 1.55 from the beginning of the wall of the heel. So from the beginning of the heel, the resultant is acting at 1.55. But from the beginning of the toe, it's going to be 1.4 plus 1.55. That's how we got what? 2.95. But we need to subtract what? We need to subtract from the beginning to the base of the center, the center base, because all we are concerned about is the distance between the resultant effect, the distance which is going to be acting vertically. Distance is going to be acting vertically, that is acting at 1.55, or you can say at 2.95 from the beginning, and your distance, the base center is what? 2.25. So by the time you subtract 2.95 minus what? 2.25, you are going to get the distance. Is this clear, or do you want me to share my whiteboard and draw? Can you hear me, Faye? Hello?
Adebiyi.
Yeah, Alpha Shield.
Yeah, exactly.
Checking drawing.
But I think if you can draw, it will be better.
Okay. And if anybody, do you guys think I should draw it, please, so that it's better everybody just understand once and for all.
Please, yes, draw it.
Thank
Thank you very much.
All right, let's do this. I want to believe everybody can see my whiteboard.
Yeah,
Yes, I can see it.
Yeah, we can.
No. So based on what we have. So basically, what is causing that problem is, let me draw. So we have this. All right. We have this. All right. So I'm just going to be drawing so we shall have this. Now, this side, I said this particular side from year to year, is my heel, and that's where your back heel will be acting. And the distance was given as 3.1. 3.1 meters. All right. Now, and I know that my total height is what? 5.5. The height of this base is 0.5. But the area of my soil itself, the weight of my soil, for me to get the vertical weight of my soil is area times unit what? Unit weight of the soil. Unit weight of the soil is 18. 18 times 3.1, because your soil, your earth material acts on the heel. It does not get to the top. That is why we are not using 4.5, which is the total base length, times, then the height is 5.5. And I think that gave us 306.9. 306.9 kilonewton. Now, after we've gotten 306.9 kilonewton, now it's always crucial that this 306.9 kilonewton is the total. Don't forget that is an earth material. Everything is going to be, the force is uniformly distributed here. So it's crucial for us to find it, to convert it to point load for easy computation. So I said for you to convert to point load, it's going to be acting at the center of this heel, which is going to be 1.15. It's going to be 1.15. 1.55 rather, Abi. By now. I'll be just shame on you, right? You shall correct 1.55. So I hope this is clear. Now, moving on. So the point is that I need to get, it was base pressure that led us to this point. We want to calculate moments of all components as the base center. Now we are pretty sure that we're pretty sure that the total length of this is 4.5. 4.5 meters. Now, the base center, the length of the base center now, let me move this down. Now, the length of the base center will be 2.25 from the toe, from this toe here. Now, let me also indicate that. Okay, will be 2.25. So let's say the 2.25 is here. So 2.25 meters. Now, that being said, so now we have our 2.25. So the point is that now this is 2.25 meters. Now, and this is 3.1, and this is 1.55. I can say that from here to here, we are giving, don't forget that the width of this one, of this particular one, was given as 0.4. 0.4. So given as 0.4 meters. I'm not putting 0, so 0.4 meters. Well, let me put 0 to avoid confusion. 0.4 meters. Now, and the remaining part is 1.0. The remaining part here is 1.0. So this is 1.0. 1.0 meters. Right? Now, so I can say that from here, I can now say that from here to here, from here to here is 1.4. From here to here is 1.4. Now, I've gotten my 1.4. So what I'm actually concerned about is that I need to get, so 1.4 plus 1.55. So I can say the distance of this vertical force. Let me put this vertical force here, which is 0. Let me put it 0.6.9 kilonewton. Now, the distance of this vertical force here, I want to calculate the distance from this point. Let me use my spotlight. Now, sorry, just a minute. Now, let's say this is my base center, right? Now, so at this particular point, this is what I'm looking for, right? And I need to get, all I just want to get is the distance between here. Let me draw. All I'm after is here to here. Let me call it X. Sorry. Let me call it X. So since I know that what? So I can say that since I know that from here to here is 1.4, 1.4 plus 1.55 will give me this place to be. From here to here will be 2.95. 2.95 meters. 2.95 meters. Now I've gotten that from here to here is 2.95 meters. And all I'm after is just here. So the only thing I just have to subtract is what? My base center. From here to here is 2.25. From here to here is 2.95. So if I say 2.95 minus what? 2.25. That will give me whatever is there. And now that's basically what we're looking for. That's X. Is it clear now? Hello? Hello?
Yeah, Taiwo, yes,
Yeah.
yes.
Very clear.
Yes.
All right.
Yeah.
Okay, so let me go back to my slide. So and then that was basically what happened here. You have 2.95 times minus 2.25, and also don't forget that this is we've taken the vertical component of our earth material. So remaining the vertical component of our surcharge. So our surcharge vertical component, we derive that one to be what? Alpha times Q, and that gives us 15.5. The distance is very similar. It's also acting, so it's the same thing. It's also acting on the E. So it's going to be 2.95 minus 2.25. So I will repeat again that the moment you are taking, when you are calculating your base pressure, is your moment of all force components acting on the retaining wall. The only one that you will not take moment is your what? Is your base, because the vertical force, the vertical weight of the base will be acting at that point that you are taking moment, because you are taking moment at the base center. But you take moment for your horizontal component of your earth material, which is your lateral pressure, that is the PA that we always look for. The vertical component is the weight that we generated from area times unit weight. For your surcharge too, you look for your moment for lateral pressure, which is what also we use Ka times Q times H. And you also use for the, you look for the what? The vertical, and you take moment using the vertical component of the surcharge too. So both surcharge and earth material, you have 4 components like that, 2 each. And the last component is going to be this vertical wall. This vertical wall, and that is all. That is 5. So whenever you are taking moments, if you miss anyone out, then you are gone. So you have to, it's not basically clear. Just know that what when you are taking moment for your base pressure, you are taking 2 vertical and horizontal for surcharge. That one, if you have surcharge. If there's no surcharge, it's very easy. You just have 3. It's only your earth material that have vertical and horizontal, and you take your vertical. Your base will not take moment about itself. And like I said earlier, the plus and minus sign gives the maximum and minimum pressure. So we've gotten our M now. We can our base is 4.5. Total base is 4.5. Our W is our total vertical forces, which we've generated. Wow, battery too low. Which we've generated. So if you use plus, you are going to get your what? Your maximum, which is 104.2 kilonewtons per meter square. If you use what? Minus, you are going to get what? 86.5. So this is your what? So your P max, which is going to be what? At the top, at the point of the toe, is going to be what? 104.2. And your P minimum is going to be your what? 86.57. So for you to now check for bearing capacity, you will now say that what? The 2 base, that is both the maximum and the minimum pressure, are lesser than both the maximum and the minimum pressure are lesser than what? 120 that was given in the question as the allowable. Hence, the section is satisfactory. So that's the design criteria for bearing capacity failure. So we'll now move to what? The design, basically. So we've done the criteria. We've done the criteria of what? We've done that. Okay, what we did earlier, all those things that we did is just to be sure that the section that we assume can actually work. The section that we chose, or the section given in the question, is actually safe for us to design and provide the enforcement. So without doing that, you cannot provide the enforcement. So the other part is how we now calculate your reinforcement. What are the things you need to do to calculate your reinforcement? And one thing is common across all parts. You need to get your design moments, because from our knowledge of all those K equal to 0.15, all those stuff, what you just need is your bending moments, your maximum bending moments. Please give me like 2 minutes. Let me switch on the gen. My system battery is. Yeah. This is just the last part. Then I think we should be done before 12. All right, great. So can you hear me now? Hello?
Yes, we can.
All right, great. I really hope you guys are following it, because this topic is not really that complicated. It's just practice. Maybe when you go through the YouTube video, we'll try to upload it today, immediately after the class, so you can go through and then. So let's now go to the design. You know, we've been able to establish that the dimensions, our assumptions can actually work, are safe to work. So let's not provide reinforcement. Don't forget that we are treating cantilever reinforcement. And when I was explaining the types of reinforcement, cantilever reinforcement as what is a reinforced cantilever retaining wall rather is a reinforced type of retaining wall. So in that scenario now, you need to provide what reinforcement, but now it's going to be in 3 parts. You are going to design them separately in 3 parts. The first part is you design your vertical stem wall, and this is your vertical stem wall. The second part is your base E. The base E is from here to here. Now, the third part is your base toe from here to here. So you are going to get a separate reinforcement for this. You are going to get a separate reinforcement for this. You are going to get a separate reinforcement for this. The truth is, and I think this is why Obaji asks this question every year in the exam, and I really feel this man will ask it because it's quite long, all right? So after you've done your assumption, right, you are not going to be designing the 3 components of the retaining wall separately. But that, to me, once you understand it, I think it's a free mark you can get. So let's go on with the design of all 3 components will be designed to witness what? The maximum bending moment action, obviously. So the point is, how can we generate the maximum bending moment for each of them? And that's where the work actually starts. How can you calculate your what do you consider to generate your maximum bending moment for each of them? So for the vertical stem wall design, you need to take note of these subtle details. The vertical stem wall design, horizontal forces are only considered. Why? Why we consider only horizontal forces? I think you don't even need to calm. Trust me, if you look at this is your vertical wall. This is your vertical stem wall. Now, the effect, the weight of the soil, the vertical weight of the soil, there's no way vertical force will act on this now. The only effect, the only thing that can act on this is your lateral wall, lateral pressure. And lateral pressure are what? Are horizontal. So is any force that is acting horizontally that can actually, only horizontal forces can act on this vertical stem wall. For you can never consider vertical forces will not contribute in design of vertical stem wall. That will be extreme over design because they are not acting there. Their line of action is directed towards the base. But for your vertical stem wall, it's only horizontal force. And we have basically 2. We have the one caused by surcharge, and we have the one caused by what? By your earth materials. So we take moment about the mid of the base. Now, don't forget that the mid of the base we're not talking about now is not the base itself. We're talking about the base of the vertical stem wall. The base of the vertical stem wall now, if you look at this, you have 0.25 from bottom. Okay, yeah. So the mid of the base, yes, the mid of the base that, well, this is your vertical, is resting on this base. So the mid of the base here, when you trace this down, is resting on, they are cast monolithically together. So this is 0.5, right? 0.5. So the mid of this base for vertical stem wall, when you are designing vertical stem wall, the first thing you have to know is that what? You only consider horizontal forces. The second thing you have to know that you take moment of those horizontal forces about the mid of what? Of the base. And the mid of the base is what? Is 0.25. The width of the base is what? 0.5. So take note of that you are taking moment of those horizontal forces about the mid of the base. And I think that should be quite evident. Instead of us using 6/3 now, straight, what we're now going to be doing now is that, look at, very interesting situation here. We are taking horizontal moment. The first horizontal moment is due to my earth material. This is 87.81 times. Now, 87.81, we know it's triangular in nature. Fine, it's triangular. It's going to act at what? H/3 from the base of what? Of where you are considering. But you are going to commit a great error if you use 6/3. Why? Because the vertical stem wall itself stop here. It's stopping at 5.5. So instead of us using what? 6/3, we're going to use what? 5.5/3. So 5.5/3 will be the what? The point of action. 5.5/3 will be the point of action of what? Of PA, that is the horizontal lateral pressure of the earth materials. But don't forget that even though this is the stats, this stats makes you take your what? Your H/3 for your triangle. So what I'm trying to explain that your triangle will not be starting from here. Based on what you have in the question. If you see what we have here now, it's starting from the base. Your triangle now is starting from what? From this top, the top of the E. That is why it's what? 5.5/3. But you are taking moment about the midpoint of this base. So you now add 0.25, which is the midpoint, plus what? 5.5/3. That will give you your what? Your moment distance. Now the second what? Horizontal is what? 8.13. This one, so you have to be careful. It's acting at the midpoint, but it's not going to be 6/2. It's going to be 5.5 what? Over 2, because your E stop here. Then you also add what? Your 0.25 to it, and that's your horizontal movement. Those are the two. So for vertical stem wall design, your design movements, we get our design movement from our horizontal movements. Our horizontal movement from what is this thing called? From our horizontal components. That is your surcharge horizontal component and your horizontal component. So by the time you add both of them together, you have what? You have 207.3 kilonewton. Obviously, we're not designing. So the factor of safety, when we are designing for Mr. Abel, we use 1.4. But when you are designing a vertical, you use 1.6. So for you to convert it to a design load, we've got
Taiwo, I have a question.
All right.
For the triangle, you said 5.5 divided by 3, right? I get that part.
Yes.
But one of 5.5 divided by 2, where do you get your 2 from exactly?
You know that your earth material is this triangle, right? The other one that will have lateral pressure is your surcharge. And your surcharge is rectangular in nature, not triangular. So my surcharge is rectangle. So rectangle from your centroid of a rectangle is what? At the midpoint of that rectangle. So it's supposed to be h/2. So if you notice that for my surcharge now, I've been using h/2. But now the h is now 5.5, no more 6. That's why I have what? 5.5/2 plus, since I'm taking my moment at the base as at the midpoint of the base plus what? 0.25, which is what? The midpoint of this base. Is that clear, sir?
Yeah. Thank you.
Good. Now, so that will only give us our service load. Since we are designing, we must multiply by our factor of safety. In this case, we are using what? 1.6. Take note that the man is using 1.6 to convert to design load. So that will give you what? 331.73 kilonewton what? Meter. Now, that's basically it. So I've gotten my design moments. See, vertical stem design, I will not lie to you, is the simplest out of the 3. Your base E and your base toe have a little complications, but it's not hard. Vertical stem design, you only take horizontal movements, you convert it to your design movements by multiplying by what? 1.6. Now your answer the answer you guess there, obviously, you use your normal design, effective depth. Now they are using 400 because it's a foundation. They are assuming 400. I think for slab we use 200 in class. Your concrete cover is 50. So these are what I think you guys should know already. Use your effective depth, use your K equal to M/FCUBD square. Your normal design from CEG 313 or 303. So you get your area, obviously you add 100, use your slab table to provide. I want to believe that this should be clear to everyone. So the only thing what I'll be focusing on in this explanation of design is how did they generate their design moments. Once they generate your design moments, use your normal slab design. Your normal slab design, but be careful that your depth now is now 400, no more 200 for slab. Your concrete cover is no more 25 or 20, is now what? 50. And you are using your bar size, they are assuming what? 20 from the onset, and you use your normal slab design, you get that. Now the second aspect of design is base yield design. So the very first thing you have to ask yourself is that what is yield? And I think I've mentioned that over and over again in this class. Yield is just this 3.1 section, and that is where your earth is acting. So automatically, what we use to design? We use base pressure. Don't forget that we've calculated base pressure earlier, and we calculated base pressure by considering what? Our horizontal component and our vertical component. That was when I drew on the board. So we've gotten the base pressure, but now where we got the base pressure, the minimum and the maximum base pressure. That means we got the minimum here and the maximum here. And don't forget that our yield is starting from here up to 3.1. So it is crucial for us to get the pressure acting at point 3.1 here. Since we have what? 2 already. We have minimum and maximum. We can use similar triangles or interpolation to get what? The one at the middle. So let's move on. And also I need to state that after we've gotten those base pressure, that base pressure we got earlier, there's still a need for us to convert it to their ultimate limit state, that is multiply them by their necessary factor of safety. All right. As such, you multiply by what? 1.6 to convert them to service load, just the way we did for what? The vertical stem design. So the base pressure moment will be gotten by taking moment of what? Of both service horizontal load and what? And vertical load at the base center. So the same way we took moment that time when I drew on the board is now the same way we are going to be taking what? Moments now. But this time around, you'll be converting your moment to what? You'll be converting your horizontal moment to service moment by multiplying it by what? By 1.6. You're going to see what I'm saying now. Now, you know that time when I drew now, I said why I think why you have to do this again. You know, when we are calculating our base pressure, we got moment, but why you have to do this moment again is because of the fact that you are multiplying, you are converting your horizontal to service load by 1.6, and for you to convert your horizontal component to service load, you multiply by 1.6. But for you to convert your vertical component to service load, you multiply by 1.0. assuming all of them have the same multiplier now, assuming all of them have the same 1.6, is that moment that we got earlier, the answer we got for that moment earlier, we just multiply the answer by 1.6. But don't forget that that moment was gotten from what? Using vertical component and horizontal component. And when I want to design, I have to what? Change each of these weights. For the horizontal, I have to multiply by what? By 1.6 to turn it to what? My service what? Service load. And I have to multiply the vertical by 1.0. That is, you're not really changing that one. So because they have two different what? Two different multiplier for service load, you have to do another moment. But once you have a proper understanding of what we did earlier, the distance should not give you problem again. All you have to take note is that just input. So for this one now, it's 7.801. We are taking moments about the base center. Don't forget, when you are doing your base pressure, you are taking moment about the base center. Based on what we did earlier, doing bearing capacity failure. We took moment about the base center. If you are taking moment about the base center, obviously. So this 8.801. So now that you know moments about the base, so you are talking about this particular base. So you are not considering the full height. All right. So it's going to be what? H/3. That is 6/3, not 5.5/3. Because you are taking moment about the base center. We're not more designing vertical stem wall. We're talking about this base. So this is 6 over what? Over 3, that is times 2. This 1.6 is just that you are converting the horizontal component, because this is horizontal component. This P is horizontal to what? To service load. Same thing for your surcharge horizontal component. It's also what? 6/2. And I think Toby John asked that question. Why is over 2? Is because it's rectangular. So I got 8.13 times 3. 6/2 will give you what? 3. Your 1.6 is also because you are converting the horizontal component to what? To service what? To service load. Now you're not getting to the what? To the vertical component. Now this is the vertical component of the what? Of the stem wall. Of the stem wall. And I believe everybody should know that this should be what? 2.25 minus what? I think this should be 1.2. Yes, 2.25 minus 1.2. Why is 1.2? Is that this 52.8 is the weight representing what? Is the weight of this vertical stem wall, and it's going to be acting at the center here, which is 0.2 plus 1.0. That is 1.2. So the same way we did the earlier one, where we say okay, 2.25 minus what? 1.2 gave us the distance for here, and this one gave us problem where I had to draw the same distance that we used, 2.95 minus 2.25. Which I draw on the board. Now, this one is basically the same answer that like what you got earlier, because we are basically multiplying by what? 1.0. And also the last one will be what? 15.5, the same 2.95 minus 2.25 times 1. So the only thing that basically changed from your movement that we did for bearing capacity is that you are multiplying the horizontal movement by 1.6 each. So by the time you multiply, so let's say that you've generated that one earlier, just rewrite everything and multiply the horizontal movements there by 1.6, then add up again. So by the time you add up, you're going to get what? A new maximum moment, which is what? 149.7. You will now use your what? Your 6m over b plus something over b square, plus or minus something over b square, will give you your maximum and your minimum. When you use plus, that is your what? Your maximum. When you use minus, that is your what? Your minimum. So the maximum here is what? 139. So the maximum acting here is 139, and the minimum acting here is what? 50.63. Now, you know when I was talking, I'm actually going back now. We are designing our U. We are designing our U, and to design our base U, we are using our base pressure. Now we know that the P minimum, we've gotten the P minimum here. So there's a need for us to get the pressure, the base pressure at 0.3.1. So because we already have our P minimum and our P maximum, that is pressure at 0 and pressure at what? 4.5. We can easily what? Use our what? Our normal interpolation or whatsoever to get our what? Our P at what? As 3.5. Our P at 3.1 rather. We're going to get there. Now, let's not look at this. You know what that man did now? If we want to design, we've gotten our P, okay? This is your pressure distribution. We've gotten our P. Let's move on. So the ultimate limit base pressure will be used to compute the design moments. So how are we going to generate our design moments from our base pressure? Note that the U is just a segment of the base. As such, the pressure distribution at the base of the wall must be accurately sectioned. So this gamma is just basically saying that you have to know that you are taking just 3.1 out of what? 4.5, because that is your U dimension. All right. Now moving on. For the given question, each dimension is 3.1 out of total. All right. I think I explained that already. So, and this is basically what you have here. You have this here. And this is your P minimum. This is your P maximum. So at this point is where we have 3.5. This dash is just indicating the center. This point is where we have 3.5. We are going to see how that will be deducted. So the diagram here shows the pressure. Now looking further, fantastic. Now looking further, you will see what? A small triangle in the trapezoidal shape. So if you look at this now, this is my U, right? So the man decided to extend this, instead of stopping here, decided to extend it to this particular base center. So for you to easily split this is a trapezium. From here up to here is a trapezium. So I can split my trapezium into what? A rectangle and a what? And a small triangle. Please just take note of this image I'm explaining, that you can easily split what? A triangle and a rectangle and a what? A small triangle. We're going to apply it very soon. Now, so further expansion now, based on what we have now, the man to me, I think just for safety, normally our E is supposed to be what? 3.1. But I think for further safety, the man extended it to what? To the center. That is, you are just basically over designing. Who they write for my screen? Adebiyi. So you have 3.1 plus 0.2. Don't forget that the vertical wall is 0.4. So the center will be what? 0.2 plus 3.1. So your total yield now is not 3.3 as opposed to what? 3.1 that you have here, because I think the man is just trying to what? Design to design you far just like over design for factor of safety, I guess. So you can easily use your what? Your interpolation. You know, we already have the pressure at we have the pressure at, how will I put it? From interpolation, we can get the pressure at this point to be what? 65 from 35. Since you already have the pressure at 4.5, you have the pressure at what? At 0. So you are getting the pressure at what? At 3.3. So you can interpolate to get your what? Your 65.5. And that's basically the magic happening there. Now that you've gotten your what? So how do you now get your design moment? Don't forget that we got our base pressure first. So it's our base pressure we will now use to what? To get our design moment. Now, what we are going to do is assuming that clockwise moments are positive, we are taking moments about the wall center line for vertical loads and bearing pressure. So what we are basically doing is that for us to get our design moments when designing our U, when you're designing your U, for you to get your design moments, you are going to be taking moments, your base pressure that you got, you are going to be taking the moment of your base pressure about the center vertical line, and also you're also going to be taking the moment of the vertical load. You know, if you could recall that when we are designing for vertical stem wall, that is when we are designing for this particular side, we only consider horizontal components. But when we are designing for our base, whether it is you are designing or it is two you are designing, we are designing for your base. What will make you get your design moments? There are two things. First, your base pressure and your vertical what? Your vertical load. As opposed to your vertical stem wall that will use your what? Horizontal what? Your horizontal load. We neither use what? Base pressure, nor did we use what? Vertical load. But for this one, we use both vertical load and we're also going to be using what? Base pressure acting on that what? On that base. Now, that being said, our vertical load obviously from this wall itself is having a vertical load, this base the base itself is what? Is 54, right? The base itself, the total weight of the base itself is 54. But you have to be careful. Since the total base of the base is 54, what will be the weight of your E? Your length of E is what? Is 3.1. So you have to know that the total weight of your base will not be 54 here. It's going to be what? 3.1 over 4.5 is a proportion of what? Of your total. 3.1 over 4.5 will give you the what? The ratio of what? Of the weight of your what? Of your E. Don't forget that you have to remove E from what? From your toe and from this vertical what? Vertical. So we have 3.1 over 4.5 times 54. Now, you are taking moments about the what? About the center line. This center line that we're taking moments is about what? About the mid vertical line. And that is 0.2 here. This particular point, 0.2. This particular point here, 0.2. Let me, I think Sheung indicated that. If there's any for me to draw, if you don't understand, I can always draw. Let me just, so this is the point, this is the line that we are taking moments from. This is the line we are taking moments from. Now, since we are taking moments about this particular point, that is this line where we are taking moments for. Now, okay, we have 54 times 3.1 over 4.5. That is, I've gotten my base weights, my base E weight, not my total base weight. So my base E weight now, which is the vertical component, obviously, is what? 54 times what? 3.1 times 1.65. Where is 1.65 coming from? Normally, please take note of this, because for example, the man was consistent with this. I think is quite wrong, but it was consistent. So I noted it down. You are going to see that very soon. Now, normally, your base, your 3.1, let's say this 3.1, 3.1 stop here. 3.1 stop here. So 3.1 is supposed to act at the center. Your weight, the base E weight is supposed to act at the center. It's supposed to act as what? 1.55. 1.55 plus 0.2 is supposed to give us what? 1.75. But whenever the man is taking Whenever the man is taking movement of what? Of heel, or movement of toe. Whenever he's taking movement of heel, and because of the fact that we are designing for heel, it doesn't add 0.2. It's going to add half of the distance. And the half of the distance is what? 0.2 over 2. This is quite complicated because trust me, there's no justification for it. See what I wrote here. I said, note the subtle details with the distance computation of the vertical base load. Vertical base load, only vertical base load that are just, I said it seems quite unjustified, but the man was consistent with the subtle details. All three is designed, as you see below. So please take note that normally it's supposed to be 0.2 plus 1.55, but the man is using 0.1, that is half of what is supposed to be in this particular place. So let's say this length is in exam now, they give us this length as 0.6. Obviously, it's supposed to be what? 0.6 over 2 is 0.3. It's supposed to be 0.3 plus 1.55. No, the man is going to take half of that. That is 0.15 plus 1.55. But in this case now, it's 0.2. So it's taking half of that plus what? 1.5. That's why we have what? 1.65. But the remaining others make sense. They are the normal way we do things. For my vertical edge, we're only taking vertical and base pressure. For my so we are still taking vertical for now. We've taken vertical base load. Now let's take vertical base pressure. And vertical edge pressure rather is 306.9. But you also have to remember that your vertical edge pressure is acting directly on what? On 3.1. So it's very clear that it's acting on 3.1 and it's acting at the center, which is what? 3.1 over 2. So it's acting at 1.55. But because you are taking with respect to this particular line here, which is 0.2, so it's going to be what? 3.1 over 2 plus what? 0.2. That is 1.5 plus what? 0.2. So normally this one is supposed to be 0.2, but the man is using 0.1, taking half. So, but this one is 0.2. The next one too, for your surcharge, 15.5 is acting at the center. That will be what? 1.5 plus what? Plus 0.2, right? Because you are taking. Then the most confusing part of this is this aspect. When you are taking your base pressure, movement, don't remember that because I told you that the man extended it here. The diagram, the first diagram up here, look at where the man is taking the base pressure. So the man is not stopping the base pressure at the ending of the heel. He's taking it to the center line where we are taking movement for. So you need to calculate the pressure at this point. The pressure at this point is the pressure at point 3.3, which we've gotten from interpolation, right? And from interpolation, we got that pressure to be what? 50.63, right? So at this point now, from interpolation, we know that this length here, this is the pressure distribution. This is the minimum. This is 50.63. This is the minimum, 50.63. Apologies, that's the minimum. The maximum is what? 139. Now, this particular place that we put X, you get it from interpolation to be what? 65.35. But then, if you have to take this 65.35 and take moment, it will be quite complicated. Once you know that you are only considering what? The pressure you are considering is just from the minimum up to the center. This is the trapezium. You can split this trapezium into two. You have a rectangle up and a triangle up, a triangle down. So this rectangle, you can easily take the area of rectangle. The height of the rectangle is what? 50.63 times 3.3. 3.3 is what? Is the base of the rectangle. When you take the area, it's going to be acting at the base of as the midpoint of what? Of 3.33. So that's why the moment of this particular rectangle is what? 3.33 times what? 50.63. So 3.33 times 50.63 is basically the area times is acting at the what? At the midpoint. So the moment will be what? 3.33 over 2. Now I'm going to take this again because it may seem confusing. Now the other part that you have to be conscious of is we've taken this up part to be rectangle. This downside is triangle. Now the mistake you will do is that if you use this full S length, because you've considered a part of this place which is 50.63. So 50.63 here is also 50.63 here. So the only part, your height of the rectangle will just be this small part. So you have to subtract what? S minus 50.63 will give you the height of the small rectangle. S minus 50.63. That will give you the height of the rectangle. So that will be what? So you know that what? This is, you have your S is 65. Your S here, oh, I think for your S is not 65. Your S is 115.98. When you use calculator for interpolation, it's 115.98. Sorry, I've been saying 55. So the total length here is 115.98. 115.98 minus 50.63 will give you the remaining what? The remaining height here. And that's why we have it here. Now, don't forget that this is not a triangle in nature. So for you to calculate area of triangle, that will be what? Half base times height. So you have half, that's where you have over 2 here, times 3.3 times. You have to be careful because this is a what? Because this is a rectangle, this is a triangle. Your center to be what? B over 3 from this place. Because this is what? This B over 3. So this particular 3.3 over 2 is supposed to be 3.3 over 3. So it's supposed to be 3.3 times 3.3 over 3. So Sheon did mistake here. It's supposed to be 3.3 over 3, which I think is corrected for the whole design. At this point, let me pause because I know it's very complicated. So if you are, should I recap or should I draw? What should I do to make it clearer? Do you guys think I should draw?
Taiwo.
Yes.
According to the calculator, the x there is 65.35. Then how do you not get 115.98?
So it's not 65.35. So
Okay,
let's say
maybe there's a mistake.
No. Like let's say this 89.127. I think this particular 3.3 over x equal to 4.5 over 89.12 is a computational error from it's not for the base pressure. It's not for the base pressure. I think this 89.12 is from our pressure. I don't think it's from the base pressure. It's from our lateralized pressure. Normally, what you're supposed to use here is 50.6 and 139.75. So try to use 50.63 and 139.75 to interpolate. Now that is at point 0, you have what? 50.63. At point s equal to 4.5, you have what? 139.75. Now in between those two, put s equal to 3.3 there. Our normal interpolation. Let me share my whiteboard. So you have something like this. Let me try. I'm trying to clean up. So you have something like I'm pretty sure this will come as an example. So based on what we have now, look at what I'm trying to say. To be sure, we have this, right? So I'm not saying that at this point, this is the way you know the way you draw your normal interpolation now. So let's make it. You have this. You have this. You have this. So our distance, the minimum side, I call it 0, right?
Yeah.
Now I'm looking for it at 3.3. This is what I'm looking for, 3.3, and the maximum is what? 4.5.
Okay.
So I think that is 9.1 to that Sheon use is not correct. Now, if you check your stuff, the pressure at the minimum, I think it's 50.63. Am I right? 50.63. Then the pressure at this, let me quickly check so we can get.
189 point something.
Is 139.75. All right, 50.60 and 139.75. So we have 139.75. Oh, wow. So we have 139.75 coming. Test. So here is 139.75, right? So we are looking for here. You can call it, let's call it S for now. From your normal interpolation, you have S minus 50.63, right?
Yes.
All over 139.75 minus 50.63 equal to, right? So you have 3.3 minus 0 all over 4.5 minus 0. So you have basically S minus 50.63 all over 139.75. Let me press my calculator here, 139.75. Are you with me?
Yes, I'm with you.
That is 89. I'm machine only day class. Mad, I go watch YouTube video.
No, we are still here.
We have 3.3 over 4.5.
We are still here.
All right, sir. So we have S minus normal interpolation now. So by the time, so you are going to be having S minus 50.63 equal to 3.3 over 4.5, that is 0.733 times 89.12, right? We say times 89.12, and that will give you 65. Oh, I see where the problem is. You have 65. You did not add, then you have to take, you have 65 points.
The answer is X is 115.98 or so.
Yes, that was
Exactly.
good. Same thing.
5.35 plus. Can you see that interpolation will work there? So it's just, that's why I didn't bother doing it. It's just a normal interpolation. But I understand that, and the way Sharon wrote it is not that quite clear. But his note is very sufficient though. So this is yes.
I think what the problem I just have there is the way I like identified my diagram.
I figured not meant to 65.
Yeah, it's still the same thing.
Yeah,
the way I like
that was why I said it's not that clear. I never said it's wrong, sir.
Yes.
All right. So just a minute, please. I call it. Okay, so that's 115. So we've gotten that is kilonewton per meter. And while we are using 3.3, normally, you know, our base E is supposed to be 3.1, but the man is extending it to the what? To the vertical line center. I think for better design or so. This part. So I can share my slide back. Ah, wow. How many minutes that's in the line? So we have this. So that's basically where so now we're not sure that this length here. See where my mouse is moving. This length is 115.98. Now we split it into rectangle and triangle. The rectangle already gave us one, and we already used 50.63 times 3.3. That gave us the area. Then we take the moment of that area. That will be at the midpoint. That is why we have 3.3 over 2. So that's why you're having 3.3 times 50.63 times 3.3 over 2 here. Then the small part remaining for the base pressure. Don't forget, when I started, for you, I'll keep on repeating it. Two things are taking moment. Your vertical forces and your base pressure. So this is the total base pressure up to that point. And that was what we split it into. We split it into our rectangle and our triangle. So the small height of the rectangle remaining will now be our 115 minus our 50. It will give us this small height. We know the base here is what? 3.3. So by the time we calculate area is what? Half times 0.5 times the small height here, which is 115 minus 50.63 times 3.3, all right? And that's why you see 115 minus 9, it's all over half, times 3.3, times 3.3 over 3. It's supposed to be over 3 because normally this is the area. When you do 115.98 minus 50.63, it will give you the height, Abi. So the height times the base all over 2 is your area. But the moment from this point should be over 3. Should be over 3. So this one should be 3.3 over 3, not 3.3 over 2. Please take note of that. Yeah. So also, the way we generated our movements now, right? Mike, I let me miss that person. Chris Wood, Richie or something. So the way we generated our movements now is that we use, I'll repeat it again, for E, use your vertical forces and your base pressure. When the complication starts from is your base pressure. Now we'll be able to do the interpolation. I think that should be clear. And now, once you see this diagram clearly, note that even though your E is stopping here, the man decided to extend it. Now, another subtle details I said you should take note of is this particular thing normally is supposed to be 1.75, but the man is not adding 0. This distance here is supposed to be 0.2 plus your half of here, but the man is taking half of this distance, and it was consistent when he designed E too, because you and Toe design have, when he designed Toe rather, you and Toe design are very similar. So since when I noticed that it was consistent, even though these news very well are not justified, please take note that whenever you are using the weight of your base, that is the only thing that is affected. To take moments, you are going to use what? 0.5 of your vertical space in between that vertical stem wall. And also you take note that when you're using the weight of your base, obviously it's 3.1 over 4.5. It's a segmented part because you are not considering your total weight, your total base. You are considering just the E. And the E is what? The dimension of the E is what? 3.1 out of 4.5. I guess that should be it. So it got the moments there. So immediately we got our moments, then you use your normal what? Your normal base, your normal this thing, you got in your moment, do your normal this thing, your normal slab design, and you get your answer. Now,
I have a question, please.
Okay, sir.
Since you said we're dividing 3.3 divided by 3, I was going to get the same two. I was going to get the same answer. These 232.7.
That she got.
Since we have said there's a mistake that we are dividing by 3, not by 2.
Divided by 3. I really when I was going through it sincerely, I think Sean and the man got the same answer. So probably he must probably corrected it and he didn't change. But I'm 100% sure, even if you check the man material, it's over 3 that is there. So even if you get a different answer, I can't really remember if Sean and the man got the same answer, but I think so. But if you get the same answer, different answer, and use over 3, I'm 100% sure that your over 3 is the one correct because it's a triangle. Look at this is where Sean is doing this. We've taken this small part. Is this upper rectangle that should be over 2? Abi, is this upper rectangle that should be over 2? This small part is a triangle. So if I want to take moments at this base, this is the base. So the centroid of a triangle, of the resultant of a triangle is what? B over 3 from the h over 3 from the base point. So this length is 3 over 3. So by the time you divide it by 3, you are going to get so. And this place like this part, last part, supposed to be over 3, not over 2. I just wanted to ask another question.
Yes, Sheon got 232.77 and the man also got 232.77. So it's correct.
Maybe Oti Jomo. Sheon did this class. Sheon, do you accept that this is wrong?
Mr. Taiwo, I can't really remember, but I'm sure what I did is correct. Yeah, I don't know, sir.
He got the same answer as the man, 232.77.
100% sure. Say probably when he was doing his calculation, he used over 3. Like 100% sure that place should be over 3. Like look at it's small triangle that Sheon is taking the moment here. All right. You know what will happen? Let's press calculator.
He got 232.77. He got 232.77.
If you use over 2, is that what you're saying?
The man used over 3. Yes, the man used over 3, and he got 232.77. So it's correct. I think it's
supposed to be a
error. Maybe
a typo error from Sheon,
but he used the right computation. Yes.
So, but scholar Joe money any notes. How come I come back to where you got the same answer?
Taiwo.
Yes.
Please, I have a question.
All right, sir.
Regarding taking moments about the hill, I understand we used our vertical forces, which include the soil and the surcharge, and we also use the base pressure. But what I really understand is why are we using the weights of the base when we are taking a moment about the hill, which is the part of the base itself? Why are we using the self-weight of the base to take moment about it?
That's a fantastic question. One thing I want you to realize is that the weight of the base, how is it going to be acting? Is it vertical or horizontal? Can you answer that?
Vertical.
Obviously. So it did not change what. So what is basically taking moments there is your vertical force. So all vertical forces are taking moments. So the weight of the base itself is a vertical force. Are you with me? So the weight of the base itself is a vertical force acting at this particular center. Or because you know that normally this total base, the vertical force should be 54. Now because you are only taking E, so 3.1 over 4.5 will give you what? The vertical weight of this section alone, which is going to act at the center of this 3.1. Are you with me? So it's a vertical force. So it's going to take moments at this center line. The only vertical force that will not take moments is the vertical force of your vertical stem wall. And why that one will not take moments is that because of the fact that the vertical force of your vertical stem wall coincide with where we are taking moments. So the distance here will be 0. That is why so all vertical forces are taking moments. Are you with me, Yabo?
Understood.
Yes, sir. So, like, if you can understand, if tone are small, tone is just that. Tone is simple, go. Tone, this is toe. What is acting? Is there any vertical force acting on toe? Surcharge is not acting on toe. The earth is not acting on toe. The only thing that is affecting toe is the only vertical force acting on toe is only the weight of the toe itself. And I think the question that was asked, I think is the coincidence makes sense for us now. Look at us now. Obviously, we're using a segment of the toe, which is 1.0 out of 4.5, right? We're also using pressure distribution because the same way we draw a pressure distribution, we are going to be drawing a pressure distribution for the toe up to the center too. So importantly, only the base pressure. So the only vertical force that will be considered here, apart from the normal base pressure that you are going to use, obviously, that is acting on the base. The only vertical force here is only the base weight because the earth is not acting on the toe. The earth is acting on the heel. The surcharge is also acting on the heel. So it's only the base weight. And that base weight itself is the segment of the base weight, which is what? 1.0 over what? Over 4.5 times 54. So those are the three things. So one vertical force, that is your base weight vertical force, and your base pressure. That's what will get that's what will give us our design moment for our toe design. Now you will see shown now, you see where it corrected is over 3 now. Now you will now see this is minus 54 over 1.0. Now this is supposed to be 0.5, right? The center of this base weight is supposed to be acting at 0.5. 0.5 plus 0.2 should give us 0.7. This same must still use plus 0.1. So it took half. That's why I told you that even though it looks unjustified, it was consistent with it. Normally it's supposed to be plus 0.2. The same way, look at now. I don't know if you get what I'm trying to say. Normally this is supposed to be the weight, the resultant of this toe weight is supposed to be acting at 0.5 here. Then we are taking it at the center of this 0.4, that is 0.2. But whenever the man is taking the moment for the base weight itself, when he's designing weight and base, he used to use half of that half itself. It was consistent for two, it was consistent for him. So I don't want to believe that is a sheer coincidence. I want to believe there's a reason for that, which I don't have a justification for now. But take note of that. In exam, that is where I will use it back to back.
Taiwo, I also noticed something from the explanation you have been giving, that you know the way you explained it, that he took the length, then the half of the half, right?
Exactly.
The way I see it is, you know, since the pressure is at that, or the moment is, we are taking it with respect to that, the center of the vertical member. Yes. So yes. I just see it as calculating the total length from the end to the middle of the center, now finding the half of it. You understand what I'm saying?
Oh, I get.
So it worked for me that, the previous E that we are designing, 3.1 to the half of 0.4, that is 3.1 plus 0.2, that's 3.3 divided by 2 to give us 1.65. For this one too, 1 plus 0.2, that is 1.2 divided by 2 to give us 0.2.
Oh, fantastic. So yes, thank you so much for that. Yes, yeah, you're actually correct. Like, let me now add one important detail that will make this make sense. What you just said make me understand it well now. It's going to be 0.6. Now, I can see what the man is doing. Don't forget that this other one here, this base pressure, 115, or let me go to my E. My E, you see what I'm trying to say better before I use that one. Now, so look at this 306.9. We are sure that our weight, the earth is acting that on top of 3.1. That is the total, that is the distance, the horizontal distance of that weight. We are sure. Same thing for 15.5. We are sure. So is this one we are going to take? So the uniformly dependent load of this one, the length of the UDL for my earth is 3.1. So if I take the half of that, then I will add the remaining 0.2. Same thing for my surcharge. But for this one, you have to understand that because the man is extending it here, So now you know the contradiction in this thing is that what the man did was that even though it took 3.1 over 4.5 to represent the weight, a segment of the weight, but he's taking his movements, knowing that since this base is continuous and I'm stopping here, so he's taking his movement. So he's calculating the movement as if he's using 3.3 over 4.5. So to me, based on what he did now, the weight itself, that is the UDL, the segment should be 54 times 3.3 over 4.5. But don't do that. Your E is 3.1. But based on what he did, and silence, I don't know if you are seeing what I'm saying, is that he's using as if he's using 3.3 over 4.5. But then I said, let's just take note of that he's using 3.1, then he's extending it.
What you have said, that when we're designing for the vertical member, it was like we cut it out of the whole retaining wall. It was like we disintegrated from the retaining wall. So what I see there is that I don't know, maybe it's just my mind, but since we have designed for the vertical member separate, the horizontal member, which is the toe and the heel put together, the reason we'll be taking the actual 3.1 over 4.5 is because it's like that is the actual design.
That's
I don't know.
that's the heel. Yes,
That's the actual design. Why that distance is just because we are taking moment about that point. Do you understand?
I get. But the truth is that, guys, just take note of that. If you know that what you understand is half of half that I explained, take note of that. If you understand Silas' own, take note of that, so that we will not add further complication to this already complicated design. So that's basically it. And then
Thank you very much.
So basically for our toe, we follow the same precedent, but now our toe only base is having vertical. So the remaining will be what? Our base pressure. And our base pressure here, don't forget, I'm supposed to draw this to take the pressure distribution. We are pretty sure that at that center from interpolation at that center we go what? 115. 115 acting at that center. So 115 acting at that center times 1.2. Don't forget that the same way we had, I should have drawn. Let me just, because without that stuff, okay, this is it basically. So now, this is what we are considering. We are considering this last aspect. On this unshaded aspect, that's what we are considering now. So we want to use the base pressure to calculate. So this is the total base pressure for this unshaded aspect. So we are going to split it into two. We are going to have a rectangle and we are going to have what? We are going to have a rectangle, what is this thing called? A rectangle and also a triangle. But your rectangle is at this point. I don't know if you can see where my mouse is. It's stopping at this point. It's stopping at starting from 115. So your rectangle will be what? 115 times your length is 1.2. Then times, when that is uniform, then times 1.2 over 2. That will give you the moment of that one. But this smaller triangle now will not be this 139.75 minus 115. So it give you this small parts of it. So that will be so you will not see that. Then once you've gotten that, you will not take, you've gotten the height, you've gotten the base is also what? The base is 3.3, then is 1.2 times whatever you get here. That is 139.75 minus what? 115. Whatever you get here, then your times half this times height. And you now see that the distance from here will be b over 3. Come and see Sheo now. Come and see our scholar. Come and see over 3 here now. You see that was why I was pretty sure that there must have been a computation now. And that is why you have 139.75 minus 115.9. It's all over 2 times 1.2. Then times 1.2 over 2 over 3.
Yes.
Now, can you see why it's over? So you just have to be very, very, like, there's no magic here, sincerely. Like, that is basically, and now it's using 2 over 3 and not 1 over 3. You know why? Because the other one will use 1 over 3. That will be very, very careful. 2 over 3 because of the fact that, look at now, I'm taking moments about this point here.
Yeah,
so it's from the tip. It's from the tip to so my center of this small triangle, the center of this small triangle from this tip, from this sharp edge, won't be, it's not going to be 1 over 3, it's going to be what? 2 over 3 of what? Of my distance. Unlike for this one now, if I'm coming from my heel, my heel is like you're mirroring this now. But now the mirror is now from the what? From the base. That's why it's what? 1 over 3. I don't know if that is clear. And then when you go to the YouTube, try to introspect yourself. You can reach out to me, and then I'm pretty sure when some people are going through, it's going to look a bit confusing. But if you watch the video, because a lot of people have been asking questions, and we've been trying to clarify, I think everything should be clear. But after finishing the video, if it's still not clear, you can always DM me. Although I don't believe this one will not come out in. Someone wants to ask a question.
Yeah, one question real quick.
Okay,
so the moment you said we use minus 54, where did the minus come from? A map, that edge.
Oh, minus is just your convention. So taking moments about this is toe design. So this is, look at this convention now. It's taking clockwise as positive, right? Clockwise as positive. So this minus 54 is acting here. It's acting at the other side. Yeah. Now you're not considering this weight. So and you're taking moments here. You're taking moments in between this wall. So your weight is acting here. So if it's going to come, it's going to go like this. It's going to go anti-clockwise. And that's why it's what? Minus. So it's just your convention. So like the weight is here, is on top of this side. So if it's going to go, it's going to go like this. But for your heel, the weight is on top of this other side. So yeah, so that's basically for that one. Thank you for that question, sir. Yeah, so that's basically that you do your normal design. You've gotten a moment to do your normal design using your slab table, and then that will be all. So if you have any questions or anything, you can still ask, but then I think our time is far spent. And then we're going to upload it almost immediately. My advice is that you can just go through. Don't try to probably understand or practice because we are doing OBJ tomorrow. Unless the man probably sets it the way it sets, he narrated and CEG 501 narrated his own. But one thing I'm sure of is that this will definitely come out in the exam. And I really hope this video will, for those that are watching YouTube video, will help everyone to probably get it right in the course of the exam. All right, thank you so much. God bless.
Thank you very much.
Thank you very much, Mr. Adebiyi Taiwo. It was a privilege.
Thank you, Mr.
Thank you
Taiwo.
very much.